Hello guys, welcome back to Techdose, and in this video we will be looking at the design and architecture of Kafka. We will be doing a detailed analysis using all the possible trade-offs using real-life use cases. This video is taken from our system design live course which we take on the weekend. So in order to be a part of it, you can WhatsApp us on this given number. Let's start the session now. Understanding about where Kafka is used, and then we will see what is Kafka. So according to their own website, if you open Apache Kafka's website, according to their own website, they have mentioned that in the Fortune 100 companies, all the manufacturing companies uses Kafka. So that means 10 out of 10. All the manufacturing companies. Example, I can say Samsung, which is a chip manufacturing company as well as mobile manufacturing company, network related company, machine learning, all the things they do. Okay, vision and all. They use 10 on 10 Kafka, all the manufacturing companies in the Fortune 100. Then if we go to the banking sector, then in the banking sector, 7 out of 10 is the usage of Kafka. And in the banking sector, you have D Shaw, JP Morgan and all. Okay, Morgan Stanley, all these companies uses Kafka. Then insurance company, in the insurance company, 10 out of 10 is the usage of Kafka. So example of one of the insurance company can be MetLife. Okay. Then in the telecom sector, 8 out of 10 usage of Kafka. Example, you can say Airtel, Verizon, Geo, anything like that. Okay. This is from their own official website, and this is for the Fortune top 100 companies. And this is the usage of Kafka. So the minimum usage is in the banking sector, which is 70% usage. Other than that, you will find a lot of usage in different sectors. Now, this is on term of high level, why if Kafka is more important than any other design topic. And now we should understand about what is Kafka. So as then this is stands for like a distributed messaging system. Distributed messaging system. Okay. So all the designs that we will be discussing will be distributed in nature. So how to do messaging in case of distributed system? More specifically, if we have to define, then Kafka is basically an open source. It is open source distributed event streaming system. Distributed event streaming. Now, the meaning of event streaming is whenever an event hits, or it is used to transfer one event from one side to another, from one component to another, or from one service to another. So open source distributed event streaming platform. Okay, so it notifies about the events, and this is used by, as I said, thousands of companies for high performance data pipelines. So when you want to make high performance data pipelines, where you can also perform some ETL transactions, where you want to extract, transform, and load all these things you want to do on a streaming platform, then Kafka can do it. It will provide you tools for that. Then if you want to do streaming analytics, that on the go live analytics you want to perform, and based on the analytics you can change your decisions. Like you want to track the load on the system, and depending on the load, maybe you want to allocate more resources or deallocate resources. If you deallocate resources, then you will be saving on cost. If you want to allocate resources, you will be incurring more cost. So it will be kind of streaming analytics, where the ongoing entire process has to be monitored, and then you are making decision on the go, right? Then I mean, you can think of any application like that. I just said about load tracking, which is used in the cloud engineering. Then you can think about data integration. You want to visualize the data in some way, and you want to take the input from different services, like how many people are currently traveling from one city to another, or you want to do some kind of live tracking, then Kafka is very useful. And you can take input from different services, like live location service, then some other service if you want, what they are purchasing, where they are placing order, what is today's weather, maybe what is the traffic situation. So all these things you can keep on fetching as a live stream, because these are all live data. Anyone who wants to see about the traffic is interested about the current traffic. Mostly we 99% of the time, I mean, we are not interested in the traffic for what was the traffic last day at 11 p.m., but we are interested in what is the traffic now if we want to move. So this is real time usage. Okay, so data integration may be required there to show you the result. You will just see the final result, but the input may come from different services. Then any kind of mission critical application where time is very important, you can consider the usage of Kafka. So for what it can do overall is it can collect and deliver high volume of data with low latency. And generally we perform the streaming of log data, but you can also stream any other thing. So it can collect and deliver high volume of data. I will say high volume of log data with low latency. You can have any other data too, but generally we play with the logs whenever we want to do data integration or analytics. We want to see what the users are doing. So logs can help us do help us monitor all those things. Now, now, so you can say that Kafka is used helps in the log processing of the data pipelines. Okay. Okay. So Kafka is useful for both online and offline message consumption. Okay, you can read more about what is online and offline message consumption if you are not really sure about it. Some history about Kafka. Some history about Kafka is it was developed by LinkedIn, and it was made open source in 2011, and currently it is being managed by Confluent. You can check it out on their website. So it was developed initially by LinkedIn and made open source in 2011, and then passed on to Confluent for management. So Confluent takes care of Apache Kafka. Okay. Now, what are the type of data that we can see is handled by Kafka? All the social media data is handled by Kafka. So if you want to design any social media platform or even booking platform like GoMMT, Make My Trip, Agoda, then uh, any flight booking system, Clear Trip, or hotel booking system like Airbnb, and if you want to design even Instagram, Facebook, or anything which moves data in real time, and require data streaming, analytics, and certain kind of updates that you want to perform as quickly as possible over the data pipelines, then we will use Kafka with that. So the use case is very wide, and let's see like some of the use cases. So first type of use case I will say is user activity events. So in the user activity events, I mean, let's say user login. When how many times user are logging in, when are they logging in, right? The notification for if certain user is logging in, you want to monitor how many people are watching Disney Hotstar at any given moment, and you see that number there, 1 crore, 2 crore, something like that. So this is like how many people have logged in and watching the watching the video, isn't it? The live stream. So this is also maybe taken as the current logins. Then how many page views are happening? Okay, even in real time, you want to track if a certain video is being watched by how many users, and then certain other video you also want to track it is being watched by how many users. Let's say two different football matches are going on, and you want to track how many people are watching which of the match. Depending on that, maybe you will be charging your different rates for advertisement, depending on how many people are actually viewing that, how many clicks are happening in real time. So if you put ads on Instagram, then you will be able to see how many ad tabs are there, and all the different type of analytics, like in Meta Business Suite. Since I use it, I know it in detail. I think you guys do not must not be using it. So you have all the analytics present there. How many people have watched it completely? How many people have clicked after watching? How many people have actually messaged you? And things like that, which will actually help me uh, see how successful was my ad campaign. This is just one example of clicks. Okay. Then you can have sharing. How many people shared your YouTube video? You will see that in the section. Okay. I mean, in every video, you will have all this information. Then about comments. If somebody is commenting, maybe you want a notification about it. You don't want the notification later, but you want it in real time if somebody is commenting, right? Then you can have search queries. These are all real-time use cases, right? You want to update the search query depending on the new incoming information. Like, let's say some real-time information is very important, like in news about some politician, which is very hot topic right now. You don't want to even miss few minutes on that. The first one to show will actually get better ranked on Google as well. So you want it to be as real time as possible. You don't want to delay this information. So your search queries will show different result depending on how fast you are updating. Okay, so these all things are important. These are all user activity events. Then you can have operational metrics. Operational metrics. As I had given you the example previously, this was like call latency check. These are all monitoring features. Or you can think about any kind of monitoring feature, real time monitoring feature, real time monitoring feature monitoring. I should say real time feature monitoring. Whatever you want to check the real time load on your system, you can do that. You want to check the latency of your calls in real time. Currently, what is happening, you can do that. Like all kind of task manager task, you can also track up across the distributed system. So it is nothing but all the services have to stream their current logs, what is happening with them. Kafka takes do log aggregation. So they will take logs from different sources. It will do log aggregation. It will do certain kind of processing that you define in the data pipeline. That if you get the input from the sources, then you have written a data pipeline which will have input, and you want to perform certain actions and give out certain output. Simple process, right? So in this way, uh, unstructured data or maybe structured data from different sources are coming, and you want to represent it in a different way. And the pipeline you write is kind of a data transformation pipeline, and you can use Kafka for this log aggregation and producing certain output. You can have one or more output too, going to different services. Okay, now third, I mean, understanding the use case is very important. But even if you don't understand it right away, maybe at the end you will see by reasoning why these are the use cases. Right now, I'm just saying about these are the use cases, right? You don't have to learn it. I think by the end you will understand. Then you can track system metrics, as I said. Again, it comes under the real-time feature monitoring. System metrics will be like, what is the network latency, what is the disk usage, what is the RAM usage, all these things, right? Anything can be system metrics. You can check it out in the task manager. But if you want to monitor it across a distributed system, not just for a single system, then maybe you will want to use Kafka for the log aggregation. Okay. So you see that important use case of Kafka is doing log aggregation.
So Surya, one
Log,
quick question.
yeah.
So most of these use cases we are talking about is like asynchronous communication, right? So does Kafka also support any synchronous communication calls?
Kafka supporting synchronous communication. I think it will not be used for synchronous communication. I'm not really sure, but then Kafka, I mean, takes the input from one side and throws it on the other side, but doesn't provide any kind of acknowledgement that your job is done or something like that. So in synchronous communication, maybe you will want to uh, wait for certain action to be done and would want to have some acknowledgement on that before confirming and moving
No,
forward.
it acknowledged only one thing, that your message is published. That's it. It doesn't tell you
Yeah,
what happened to the message. It is getting consumed by some other consumer or not.
yeah, yes. We will look at it. It uses two-phase commit. I think we had covered that already in the atomicity. Okay. I mean, you may be required to read more about the transaction coordinator. So we will come to that. We haven't done anything yet. Let's see. Okay. Right. So uh, let's move on to the log aggregation. So what is log aggregation? Just in short, let me just tell you what is log aggregation. So if I have to just define it with few words, then it is about capturing the logs from different sources, then normalizing the information according to how I wish it to be seen, and then maybe I want to consolidate the data. Okay, consolidate the logs. So maybe capturing, normalizing, and consolidation from different sources to a centralized platform. So I can say from different sources, you will collect the data and make it available to a centralized platform. Okay. So this is generally done for correlating or doing some kind of analysis. Okay, log analysis or anything like that. So as I said, real-time feature monitoring is one of the thing. And within that, you will have real-time analysis and monitoring. You will have app monitoring too. So all kind of app monitoring, whatever options are available in your apps or for the developers. Then you have capacity planning. As I said, in the cloud, you will, if the load is increasing in real time, you will want to allocate more resources. So you have to track what is the usage for the time being. Then you can do multiple types of data visualization, because if logs are available from different sources, you want it to be available, then aggregate and make a bar chart, pie chart, whatever you want to, whatever kind of visualization you want. So I think you get it right, what is log aggregation, and right. So just to define what it is doing is it will first be identifying the log sources. So identifying the log sources, then you will be collecting all the logs. When you have identified the sources, you will be collecting the logs. Once the logs are available, collected, then you will be parsing the logs. I mean, this is the work of Kafka actually. Then after parsing, your pipeline will perform the processing, whatever you want, the processing or any kind of data transformation you want. You can perform it by processing the logs. And finally, you can store them or you can stream them to any service that actually requires them. So I will write store the logs. So this is the simple flow of the log aggregation. From different sources, you collect the logs, then you apply any kind of transformation you want, consolidate the data at a place, and then you stream to whichever service wants it, or if it wants to be stored, then you store it somewhere. So other services can pick from the storage directly. But generally, Kafka is better. Okay, we will come to that. I cannot make this statement right now. Okay. So I think our use case of log aggregation is quite clear. But then why do we need Kafka and why cannot we go with the simple databases? Or maybe there are many good databases which are available. So why should we go for Kafka? Any answer for that? Kafka versus DB?
Scalability. Let
Okay.
us say we want to introduce a
High
new
level
service.
first.
Yeah.
Any like any answer for like why can't we write directly to the DB? Like if I can write to DB and people can read from DB, then our job is done. And we will have ETL tools as well. You can maybe required to read more about ETL tools, which is not required. It is extract, transform, and load. So let's say, let me give you an example. Okay, so let's say, I mean, it is used in a lot of applications. So don't tell me that we have not covered certain design. And so what now? How can you design any new system when you see, right? So throughout all the classes, whatever concepts are there, you have to just, I mean, put them in a single plate. Like you have all the ingredients, right? So in this case, let's say we talk about any food delivery system. I don't know what systems, what food delivery apps are available across countries, but I think Uber Eats and Zomato, maybe people may know about it, right? In other countries, maybe they are not that famous or not available at all. Swiggy, Zomato, Uber Eats. I think you can think about any online food delivery system. Now, in the food delivery system, maybe on a, let's say you yourself started a food delivery system, then what all actions would you want? Like if you think about any food delivery system, what all actions do you want? So you want live location tracking. Simple. Live location tracking of whoever is delivering, right? You want to track them out. Then you want the status of order. If I place the order, then is it placed? Is it confirmed, or what is happening? Is it cooking, or what is happening with my order? There can be many other things. If I simply consider Uber or Ola, like the cab services, then suddenly live tracking, status of order, and again many more things can get added. Maybe it estimated time of arrival is also one of the service, maybe one of the things that you would want to track. Okay, when is it is estimated to be delivered to your home, or when do you want to when you can have the capsule, and when will you reach your destination? All these things, and you can think of many other things as well, but let's keep it simple. Now in this case, if you have developed your application and if it is being used just in a single city, let's say it is being used just in a single city, and I will take the example of what, Bangalore, let's say, and our application is just live in a single city. Now Bangalore having, let's assume that it has 2 crore population, right? I think this is what it is, right? I hope it is to 20 million, isn't it? 2 crore. So whatever. So Bangalore has this much of population. Let's say the transactions it is performing, and the things which we are using is the food delivery system. The app we are using is, let's say, Zomato, and we have, let's say, 100 transactions per second. Let's say, okay, I cannot debate about how many are happening, but let's say 100 transactions per second, 100 per second. Now, if these many transactions are happening, then you can simply write your information in the DB. Let's say that there is a driver, okay, and then what the driver will do is it will update the database. So this is the database, which is maybe the live location database. Okay, so it is maintaining the live location of all of the drivers, whoever are online. Whenever you want to be a delivery guy, you have to log into the application and say that I am the delivery person. I am now online and I am serving this order. So now you will be tracked. All your information through the application will be streamed to the database. It will be written to the database. Now, somebody who has placed the order will be streamed the data from the database, because the application knows that you have placed the order and he is the driver who is connected to you. And so since I am tracking what is the live location, so I will also stream to the user that this is the live location update. Yes, there will be some latency of few seconds, but then and that few seconds latency happens because the driver writes the data to the database, and then it is streamed to the user as well. Okay, so some latency will happen, right? If you are using a database, somewhat higher latency will happen actually, because it takes time to write information to DB, and maybe wherever you want to write the information, that may have been logged by some other system or may not be available for the time being. And this architecture is completely fine. There is no issue with this architecture. We do not need Kafka in this case. And if you just Google out how many transactions your database can handle, your database can handle 100 writes per second. That will not be a problem. Okay. But then if we are scaling our application, and let's say it became very popular, and now you have to scale your application across different cities or across one country or more countries. Let's consider only one country, and let's say we have scaled across India in all the tier 1 and tier 2 cities. Let's say we have scaled across India. Now suddenly our transactions per second can be more than 100,000 per second, because you are talking not just about Bangalore, but about all the tier 1, tier 2 cities in India. And maybe I'm just being a little optimistic. So let's assume 100,000 per second. Okay, in the peak hours. Now, if you want to make these many writes to the database, then it is bound to fail actually. So generally your database can handle few thousand writes per second, but you should not go beyond that. In most of the databases, you cannot go beyond that. Okay, and if you are choosing a database for higher number of writes per second, then maybe it will not be able to perform the other operations, other storage, indexing things that you were thinking about for a database, because database is a long-term storage and it is a persistent storage. If you also want to perform it 10 in 1, 3 in 1, 5 in 1, then it will be not giving optimal operations for other things. But mainly, it is always good to avoid high number of writes in a database per second. Okay, a database may crash. Most of the time it will crash, and if it crashes, then your system becomes unavailable, and so you lose business. You don't just lose business until the database doesn't come up, but then you also lose the trust of the customers and they will not come back. So you lose the customer base, and you lose business, you being unavailable for certain time. So availability is very important when it comes to business. Like even if I have a website and I have videos there, and if it is down most of the time, then how will you watch the video? That is a problem, right? So for that reason, we need another streaming platform, because Kafka can do more than 1 million writes per second. 1 million writes per second. And that is where it is useful. Like now, let's not write it to the DB. Now the now the architecture will change. And instead of the DB, now the driver or many number of drivers will be streaming the data to the Kafka pipeline. It will give to the Kafka component. It will do data transformation if it wants. And if it doesn't want, it will just deliver to whoever have actually put the order. Whoever puts the order have actually subscribed to get message from the Kafka. Okay, that I will come to later. I'm not explaining that right now. But in this case, the DB will always be present. Okay, I will come to that again, why DB is present. Now DB is actually, the Kafka will take the input from the driver. It is streaming to the user, and in some time it will also write to the DB. So Kafka's hardware feature is it can do a lot of writes, a huge number of writes per second, but it has limited space, and it is not developed to do queries like database. It is just like a queue where you push the item from one side, you pop the item from the other side, but you cannot randomly access the item anywhere in between. So you cannot hope to access any item just like you have access on the indexed database, that you access any item very fast based on key and you access the value. But in this case, those all features are not available. But then the important part is it is focusing on making a huge number of writes per second. And if we can do that, then we are not directly writing to the database. We are not directly writing to the database. So the database will not crash. And the Kafka will do bulk write to the database, which is very much more efficient. I will again come to this, why it is efficient. It is very much more efficient than writing one time, one write after another. If you can consider an example of TCP IP connection. So in a TCP IP connection, first you have to do three-way TCP handshake. And after that, you do data transfer. And then you say that I am stopping the connection simply. So this three-way handshake has to happen. The disconnection has to happen. And if you are just transferring one data packet per, connection and disconnection, then if you have to pass 100 such packets, then you are doing 500 to and fro motions. But if you can transfer all the 100 packet within the same connection and disconnection event, then you will just be having an overhead of 3 times here, 1 time here, plus 100 here. So simply you will be having 104 to and fro motions rather than 500. I hope you got this right. So in the writing process as well, it is not like directly you can write, but you have to prepare for writing. In the slower Windows operating system, I think you will be able to see that when you copy paste some large item, it prepares to write. It cannot just directly say that I'm writing. Prepare for write and then write. Okay, I will share the data with you, what actually happens. But coming back to our example, since databases are not made for handling a lot of writes per second, therefore we need another piece of hardware which can do a lot of writes per second. And then Kafka comes to our rescue. So it can do a lot of writes per second. It doesn't crash under huge amount of write load as well. And it will also keep the data saved for some time. Let's say you have a Kafka and it is doing a lot of writes per second. It is not as big as the database, but it is good enough to maintain the data for 4 or 5 days. But after the end of every day, it will make the write to the database. Okay, so the database is maintaining all the data. It is not getting overwhelmed by rising peaks and lows, whatever it is, rising demand, lower demand, whatever it is. But the Kafka can do bulk write on the database and everything will be fine in this system. So if you want to scale your system to more number of writes, then Kafka must be used. You cannot just use DB and get away with this. So all these applications, wherever you want to have live monitoring about anything, like cab driving system, Google Maps, and anything, whatever you can imagine. All these things have to use a streaming platform or any kind of streaming platform as well. All these have to use Kafka or anything like Kafka. If there is some other option available, you can go for it. But I mean that they have to use Kafka. Okay, so now we know why we should use Kafka and how it is different from a DB. Simply more number of writes per second, it can handle very easily, right? Simple. Now, again, I haven't covered any other application, but whatever you can imagine, like you can imagine about WhatsApp live messaging. Like if you are chatting with someone, then what is happening? You want to send your message and the Kafka will take the message and it will immediately send the chat message to whoever is connected to you, means whoever has subscribed to the Kafka. And then it will immediately be streamed to that person. So any kind of live chatting application you want to set up, chat system. So WhatsApp, Telegram, Discord, or anything you can imagine. All these have to use the Kafka component, right? Okay. So I think now you can better appreciate the usage of Kafka. It is present everywhere. But then you should know the reason why it is present everywhere. And it is very handy. Actually, you can write your own data pipeline for Kafka. So what kind of input is coming, what kind of output it should give. So some processing you want to do. If you want to do heavier processing, it will take more time. It will increase the latency of Kafka because some data transformation is required. Or what you can do is you can do less number of transactions when you are, I mean, sorry, less number of transformation when you are streaming the data, like message passing. No transformation is required. Just pass the message as it is. But then when you want to write it to the DB, maybe you want a pipeline to be written here. That maybe in the DB, I will write it in a better organized way or in some other organized way. So then you can have a pipeline between Kafka and DB. So that is also possible. Now, okay, so I think we should move on to the next part of it, right?
Just one question here.
Yeah.
So as you mentioned, like DB can take up to 100
Not just
writes per
100, I mean,
second,
it
right?
depends on the type of DB. So you will
Sorry?
find it depends on the type of DB, I said. So many DBs can take in thousands or 10,000s, and many will not even take 1,000 or it will
Okay.
take.
So let's take an example of, let's say, 1,000 call, right? And
Hmm,
Kafka, we are publishing a million record per second, right?
hmm,
So and if we build a pipeline to write the data into DB, where we are just consuming like 1,000 record every second and writing into DB, because it cannot take more than that, right? So what will happen to remaining 9,000 or 900,000, and keep
Now
piling
you
up
are
because
saying that the maybe the data will not be written fast enough to the DB.
yes.
Oh, I mean it will be written fast enough because we are doing bulk, right? We
No, no, I,
I'm
I, I totally agree. You are writing. So bulk writing also has a constraint. Like you cannot put uh, more than a certain limit into that, right? So that is also a limit. I totally agree. Like you can combine 1,000 record in one write, and then you can just write it up, right? But
Mhm,
again, there is a limit on the data transfer. So then
mhm.
how, if we are publishing a big messages onto the Kafka, so how we are going to handle that use case? Because
Hmm,
messages keep piling up into Kafka queue, and Kafka queues also have a limitation to, like, it cannot have more than certain limit of
hmm,
data, or you can say
hmm.
memory.
Okay. So for that, I think uh, you will apply transformation and maybe reduce the number of inputs that you want to write. That is one thing you can do. Another thing that you can do is you can add more databases to be written in. Another thing that you can do is in the as I said, in the bulk write, you have to perform less number of operations when you are writing. So actually the transactions, what will be the limit of writes will depend on what will be the number of transactions that you are doing. So the number of transactions will be less. Also, uh, database, whatever is the limit, it will depend on, it will have a fixed limit, but then the requirement will be always going up and down. So it may so happen that we may not be able to manage the peaks in the database, but the requirements may not always be same. Like at the night time, you will not have a lot of orders coming, but you can always uniformly write the data from Kafka to the database because it is holding back. So it is streaming in a more uniform way. So
Yeah,
it is
yeah,
able
that
to.
that part
Hmm,
that part I got it, because that's why my second question was like, if we are doing it in a stream where, like, in a uniform manner, right?
hmm,
So during the peak time, we are publishing a lot of messages to Kafka, and
hmm,
that might result, we might lose some data, or we might lose some messages in Kafka, because Kafka is again having a limit of, the memory limit will be there.
hmm.
Is it
See,
not true?
we I mean, yeah, I got your question that we have a limit in memory. But even if when we are even thinking about our system to be designed, then maybe I will not just use one Kafka broker. I can have multiple Kafka brokers. I can have region based Kafka brokers because
And we
maybe
can
many of these things, services,
Okay,
and
so you are saying,
applications will
okay,
require.
okay, and then
Uh,
then you are going into distributed again. Okay, okay, got it. No
yeah,
worry.
maybe I have not explained how the designs are actually. I mean, what is the architecture of Kafka for the time being? So let's discuss about the architecture. It will have. I mean, it is having a feature of dynamic scaling. So when it requires more, it will add on more partitions. When it requires less, it will deallocate partitions. So based on that, it has backup partitions available. And the number of backups you want to keep depends on what is your estimation about your own application, right? I mean, if I am doing wrong estimation, then it will break definitely. That's why the systems break. That
And
something
every backup
unexpected happens.
partition will add up more memory into
Yeah.
system.
Yeah, partition will
Not
add up. Okay, I think when we discuss about the PubSub model, how it works, then uh maybe we will understand this thing,
sure.
because answering it now will not make sense maybe for others. Yes, Lakush, you were saying something.
I was just trying to say that when we will be having this architecture where someone will be producing some messages on Kafka, and then there will be consumer groups. So the DB selection will be on the consumer group. So might be there are multiple
Okay,
consumer.
we will come to this discussion in a little while. Since you mentioned about the mentioning more about architecture, we have not started with the architecture, right? We are just
Yeah.
seeing high level overview of why we should care about Kafka. Let's come to the architecture discussion, then it will make sense.
Yeah, yeah.
So I cannot discuss the architecture before even myself discussing about it. Okay. So yeah, fine. Uh, okay. Hmm. Okay. Also, one more thing I should have mentioned is the latency of write is less in Kafka as compared to the DB. DB has more latency of write. So if you have more latency of write, I mean, if you are transferring any chat message or any kind of log message anywhere, then if you have more latency of write in between, there will be network latency. There will be different type of latency, network latency, processing delay, queuing delay, all these kind of delays are there. Along with that, if you have latency of write, higher latency of write, then overall latency to pass message from one side to another is increasing, and we want to reduce it. Okay, so Kafka has lower latency of write. DB has a higher latency of write. Okay, I think we got enough points just to validate our point that we should care about Kafka. Okay, this was just a discussion for why we should care about Kafka. Okay, fine. Are we good? But then the next question is, why don't we use Kafka and drop the DB altogether? Because Kafka has less storage. I mean, not just less storage, but Kafka is not an organized way of storing the data. It is just like a simple queue. Okay, and you are just following the first in, first out ordering there. But then on the DB, you can leverage the use of indexing, and you can do data transformation. You can do queries. On Kafka, you cannot do all these things. You cannot do queries and all. It is not optimized for that. It is just optimized for higher input and higher output with some kind of processing involved. But then it is not optimized for organized structure of storing the data and you being able to query on the Kafka. It is not done for that. Okay, so that is why Kafka is a complementary component. It is not something which can replace the DB. A DB is different, and Kafka helps in the entire architecture. So Kafka is complementary to DB, you can say. But the DB is not replaceable here. Okay, DB you have to use because you want to make queries, you want to do certain backend type of queries or any data analytics later on the previous logs that you have collected and organized. So those all things we will do on the DB, batch processing and all. Fine. So let's discuss at a high level about Kafka architecture. So we are starting with the Kafka architecture and we will come to that. But I think I did not say about the about proper throughput and storage. So if I have to compare throughput and storage of both Kafka and DB, then for Kafka, the throughput will be higher, but the storage is lower. And for DB, the throughput is lower, but the storage is higher. Okay. Just for a simple comparison. Then you have indexing. So indexing is available in DB, not available in Kafka. Like B tree, B plus trees, all these things you use. These are available on the DB, but have nothing to do with the Kafka. Okay. Now let's start with the Kafka architecture, and let's start with the simple architecture where you have drivers. Let's say I'm talking about the food delivery system. So you have the delivery boy or the driver. Then you have the shops. So maybe shop 1 or outlet 1. Then you have shop 2 or the outlet 2. And you have many other services from where the data is streamed. People will require data at any point of time because many people will be requiring from many different drivers. Everyone will have separate driver maybe most of the time. And then people will be ordering from different shops or outlets. So all this information will be streamed to the Kafka. Okay. All this information are coming. So this is the aggregation part. Okay. Now from the Kafka, whatever services had actually subscribed to the Kafka that I need those information from you, then Kafka will know that whenever certain information come, then maybe I have to send it to this ETA service. Let's say estimated time of arrival. So certain data to which the ETA service has subscribed to, the Kafka will publish about that information to that service. Like whatever YouTube channels you have subscribed to, when they upload the video, maybe you will be notified. But those where you are not subscribed, it will not be notified. Simple structure, right? Simply that thing we are following. Let's say you are doing fare estimation. Maybe it is raining, so they will charge higher, or maybe based on distance. Some kind of estimation has to happen before you place the order. So maybe they will require the information about your location and the shop's location and the current weather as well. Maybe weather also plays a part in deciding about what will be the fare estimation. Maybe, right? Generally it does. Then you can have real-time analytics, whatever type of analytics you want to do on whatever data you want to do for those data, you have to subscribe to the Kafka, and then they will stream to the real-time analytics. Then even DB is connected to the Kafka. So then all the information you want to write, you will be writing to the DB, and it doesn't mean you will just be writing to one DB, but then you will be maintaining maybe location in separate DB, something else in separate DB if you have normalized your entire structure. So maybe while you are writing, you are making a bulk, you are normalizing your table and separating out the information according to your own normalizations. You want to write it at the same place, you can go ahead and write it. That's not a problem. But this 1 DB doesn't mean it is just a single DB where it is writing. Okay, so this is the simple data flow of Kafka. So these guys are called producers who are actually producing information, and these guys are called consumers who are consuming the information produced by the producers. And Kafka is acting like a broker where consumers actually tell the broker that I want this information if it comes to you. Then the producers, when they produce the data and the broker sees it, broker knows whom to send the data. Just like even in the house renting system, there is a broker in the middle. So you tell your requirement to the broker gets other applications from the house owners. So the house owner application comes to the broker knows where are my clients. And so it will tell those people that you are interested. Since you are interested, so I'm telling you about this house available in our area. Simply the subscription model. Okay. Fine. Now coming back to our write, the bulk write. So I've collected some data. In the bulk write, first thing you do is connecting to the database. When you want to write, you have to connect to the database. That takes 3 unit of time. So I'm writing in terms of unit. That takes 3 unit of time. Then you have sending query to server. Sending query to the server takes 2 units of time. Then you have parsing the query. So parsing the query takes 2 units of time. So this is all for setting up the connection. This is all for preparing to write. So this is the phase of preparing to write. Prepare to write. So for if you are doing write separately, one write after another, this you have to go through all these things. Then you have inserting row into the database. Whenever you want to insert a entire data, you will be adding a tuple. So this is inserting row is 1 into the number of rows that you are inserting. Now, if you are inserting one row after another, then this n value will be 1. That means this is 1. Okay. After this, you have inserting the indexes, inserting row, inserting indices, I will say, or I will say index. So 1 into the number of index, let's say. Let's keep it same. And then you have closing. So closing takes 1 unit of time. So this is about closing to write or closing the write, I can say. Closing the write. Okay. So in this case, for doing one write, you will be incurring 3 plus 2 plus 2. This is 7. This is 2 times of n. And this is 1. So if I take the value of n to be 1, that means you are making only one write every time, but you are not doing any bulk write. Then this will be for every write you are taking 10 units of time. So 10 units per write. Okay. Now, if you are doing, let's say, 10K writes, or let's say 100K writes, if you are taking 100K writes, then you are taking 1 million or maybe 1000K, simply 1000K units of time, right? Units of time, or let's say second or ms, 1000K ms. And if you have to make all these 100K writes at once, then you will have total of 7 units time here, 1 unit time here, plus 2 times of 100,000. So you can neglect this very small, and that will be around 200K ms. You see, there is a huge difference. You have 80% saving actually when you do bulk write. 80% saving on time. So it is not just few seconds or 5 or 10%. You save 80% when you do larger bulk writes. Okay. So you can also read about this in detail, but I think it is not required. I was just trying to tell you that the bulk write is very efficient as compared to one-on-one write. Okay. Now coming to the Kafka. Even though you have a Kafka like this, but then you might be thinking different type of informations are coming. Like let's say live location information is very different than the weather information. And then if we club them together, it will become mixed, and you may not want to do that. You want to organize everything, like how in a library history books are organized at one part, geography books on one side, and this looks good and easy to search. People know if I want to search for something where I want to go. So simply in Kafka, the same organization is applied. Where have been? Yeah, so simply in Kafka, the same organization is applied, you know. So by same organization, I mean that Kafka is divided into multiple parts called topics. Okay, so let's see what is a topic. So maybe topic 1, I'm just writing in terms of topic 1 and topic 2, but you can make your own topics. So in topic 1, you can get the live location data, simple, the live location data. Then in topic 2, you can have the weather information. Okay, so this is live location, and this is maybe weather information. Both are different, completely different things. So they are organized in different topics. So you have a number of topics depending on how many different type of information you have. And everything is organized within the Kafka. Okay, I will say this is the Kafka. Now, all the producers, when they are producing the data, maybe the live locations that you are taking from the Google Maps or something, You have integration with Google Map. The Google Map will share the live location of the device and it will be streamed to, let's say, this topic. And then some other information about what is the weather in that location will be streamed to another topic. Okay, so this is how we organize based on topics. Okay, based on what type of information you are doing. But even within the topic, you may be adding the information in a simple queue, that you are adding the information from one end, from another end it is getting consumed by the consumers. Okay, so there can be multiple consumers who are actually consuming all the data. Fine. So you are writing the information. This is called a partition actually. So you are writing the information in a partition, and the partition on the other side, the partition is getting consumed. So this is actually in a sorted order, in a time sorted order, chronology. But then again, on a partition, there are certain rules that we will be going through. Okay. And it is not very useful that you just have one partition per topic, because everyone will be gathering around that single partition to consume the data. And that is not actually a good way of organizing the data and also to publish the data. Maybe it will put more load on that partition too. And maybe I want to do load balancing. If all the requests are coming for the same server, that server may crash. So if you want to do load balancing, first thing, you would want not just one partition, you will not just want one server, but you will want multiple servers for that, isn't it? Are we good? Are we good here? So this is partition 1. Then you have partition 2, P2. And like that, you will have K number of partition, let's say, PK. You will have multiple partition in this. Okay, we will come to the load balancing later, but I hope this is clear. Nobody is seen
Yeah.
in the video. Where are the videos? Everyone is like out.
No. Okay.
Okay, so yeah, so that's why we will need multiple partition. I will discuss about load balancing at the end, but you can just make it out. I think that from one server, if you want to do all the things, it will be difficult. So let's not just write on one partition, but let's stream to multiple partitions for that reason. Okay, so data is divided between multiple partition. Now you can also stream the data not to the I mean the same data may not be shared with all the partition. You may have a group or a small subset of the partition where you will send some data and some data are not sent. Like if you are sending here 1, 2, 3, maybe you are sending here 2 and 3, maybe you are sending 1 here. That can happen. Okay, a subset of I mean replica partitions will be present, but you will also know that how I'm replicating. You may replicate based on some certain kind of hash. So if it is matching certain hash, then maybe you are sending it to partition 1 and partition K. But if it is matching some other hash, you are sending to partition 2, partition 1, something like that. Okay. So I'm saying that replication will happen, but it doesn't mean that all the data are streamed to all the partition. Everyone may not have the same data. Okay. Maybe one partition is holding all the prime numbers. Let's say all the prime numbers. Another partition is holding all the odd numbers. But then all the prime numbers will be all the odd numbers. But if somebody is holding all the even numbers, somebody is holding all the multiples of 5, you will have some common data and you will have some uncommon data too, because based on the requirement of the consumers, some consumer may want to just take all the multiples of 5. So maybe you have a partition for that, all the multiples of 5. Certain group of users want to consume all multiples of 5. So you created a partition which has subscribed for all the multiples of 5. So all the multiples of 5 will be streamed to this partition. It will be storing it, and then it will be streamed to all the consumers. But it doesn't mean that the data will not be present in the other partitions. Also, this is one way. Another way could be your application is highly scaled, and so you may want different partition for different region as well. Like even in the single city, so if you have a high load in the city, then maybe you will want different partitions to operate for different regions in the same city, like north, east, south, central, and west, something like that, because you have very high number of consumers there. So that will also help you do load balancing and organize the data in different partition for the exact same topic. You are tracking location, but then I mean, you can apply any kind of logic here, like how you would want to do organization, how you would want to do load balancing, and how you can better serve the consumers. Okay, so I think we get the idea about topic and partitions. We get the idea. You can do it based on hash, you can do it based on location, you can do it based on anything you can think of. Actually, that makes sense. Whatever makes sense, you can choose your partitions accordingly. Okay, based on location, I told you already. So I think I think we are clear with the meaning of topic and partitions, right, in the Kafka, right? I hope we are done with this. So the next thing is about I mean, there are a lot of things in this. We have dynamic partition updates, then we have auto balancing and all these things. Okay, we will come to that. Now, in the dynamic partition, dynamic balancing of the partition, if you need more partitions will be added. And if you are not using certain partition, that will be removed and added to the pool. Simple. Okay, I'll not go into the detail of that. So that is about how you dynamically manage the number of partitions as well. Okay, so let's go to the next part in the architecture. If you have understood about topics and partition, then let's talk about how the consumers work here. Okay. So in a Kafka, there is a rule. I mean, in Kafka, there is a rule that a single consumer can only consume from a single partition, and a single partition cannot stream to multiple consumers. Okay, so then you will not just have few consumers. Like if there are k number of partition, you cannot stream to more than k people at a given point of time. But then I don't want to be restricted by the small number of users, right? Maybe I don't want to be restricted. I'm taking a new page. I don't want to be restricted. So if I have certain partitions, let's say clearly mentioning partition 0. So I'm just taking one topic, but you will have a lot of topics. Let's say I'm taking 4 number of partitions in this topic 1. So these are partitions are within a topic. So this is topic 1. And all the topics are within the Kafka clusters. So this is a broker entire. But I'm just maintaining that I have a single topic, but you will have many other topics below it. Okay, a lot of messages are coming from the producer side, and then there are certain consumers. So if I have just a single consumer C1, it can subscribe to multiple partitions. It can subscribe to multiple partition, but a single partition can only send to a single user. That is the rule. So let's say I have C2, C1, C2, C3. Let's say that C1 has already subscribed to 0, 1, and 2. Now C2, if it wants data only from 4, then it is fine. Let's say C3 wants the data from 2, it cannot be streamed, because a single partition can only stream to a single consumer, isn't it? Right? Okay. Are we clear here?
Yes,
So
yes.
Okay. So I have a question for you. Is it sensible that a single partition actually streams to a single user? Or is it sensible that a single partition can stream to multiple users, U1, U2, U3, but a single user cannot take from the multiple partitions? That whatever I said, like a single user cannot take from multiple partition. I just made a statement previously. You have to think about, is it a wrong statement or what makes more sense? That if there is a consumer, you can consume from multiple partition. You can do only one of the two things that I'm guaranteeing. Okay. And this is one option. Another option is the partition can stream to multiple consumers, but the consumer can only consume from one partition. What is more sensible? Just think about it.
Multiple consumers can consume from a single.
The second, for me, it's like second statement.
Okay. So
Like
So there can be
multiple.
multiple subscribers for a given topic, right?
Yes.
what?
For a
There
given
can
topic,
be
you can have
multiple,
multiple subscribers.
whereas opposite is not sensible. Multiple subscribers, multiple publishers publishing to a single subscriber doesn't sound good. But
Yeah.
you can have multiple consumers who are consuming from a single publisher or whatever it is.
Single topic.
Yeah, single topic. Yeah, technically single topic.
Okay.
One-to-many
So-
relationship.
Okay. So in the initial Kafka design, actually multiple consumers cannot consume from the same topic in the initial design. Okay, the design evolved after that, but in the initial design, multiple consumers could not consume from the same partition. But okay, could not consume from the same partition. But then one consumer could consume from multiple partitions. This was the initial design. Okay. Now there was definitely a need for the design change. You should not uh, you should not actually do this. And actually the apt thing would be multiple partitions can give to multiple users, and multiple users, one user can take from multiple partitions. Because you as a user, you as a service may want both the location as well as weather information. Because maybe you are a fair estimation service and you may want multiple informations, right? Who knows? So for that reason, there is a concept which was introduced called consumer group. Okay, so now a single consumer is assumed like a consumer group. Let's say you have a consumer group, so consumer group number 1. In this, let's say you have a single consumer. So this consumer can take input from multiple partitions, as I said. Okay, it can take input from multiple partitions. And within the same consumer, if you have another consumer, let's say C2, then it cannot take from any partition which is already taken by somebody else. So if you just have a single consumer, it is fine. But let's say, what if you have consumer 2 who needed the information from 4? Now C2 cannot actually take from 4 because 4 is already been subscribed by C1. So how can you get rid of that information? I mean, how can you get rid of this problem? Then maybe C2 will move to a different consumer group, and a different consumer group is assumed like let's say this is CG2. This is assumed like all the partitions are again unsubscribed and available to be subscribed by anyone in consumer group 2. So now consumer group 2, since consumer 2, since it needed the information from, let's say, 2 and why I've written 4 here, so maybe 2 and 3, then it can safely take that. But within the same consumer group, let's say there is another C3 available, consumer number 3, then the rule is within the same consumer group, 2 consumers cannot take from the same partition. And if you want to actually, if there is some conflict, then you move to some other consumer group. Okay, so with this concept of consumer groups, if C3 wants from 0, so it will get from 0. There is no problem. But if C3 also wanted from 2, then it cannot get it because 2 is being subscribed by C2. And if it definitely wants it, it cannot live without it. So maybe C3 will move to another consumer group. And there it can get from 0 and can get from 2 as well. It will be treated as different. So all the consumer groups are treated separately. But the users within the same consumer group can actually, definitely will have to follow that. I just go to one party. I can go to multiple partition, but the partition cannot go to multiple user assignment. So this is the current architecture. With this, you can actually directly move to a different consumer group and you will be fine if you want to read something, but you cannot get it because in your consumer group, somebody else has also conflicting what do you say, request or subscription, then you move to a separate consumer group. If there is no consumer group available according to your request, you will form another new consumer group where only you are present. Many more people will get added there. So with this concept, let's say C2 was here, so maybe I will have C4, which can take from 1, and that's completely fine. If I have C5 here, which wants to take from 0, it is fine. But if we have C6, if we have C7 within the same consumer group number 2, all the partitions are already taken. So they will be waiting. They will be waiting. They cannot consume. And this is also one way of keeping backups. Like, let's say these consumers are actually worker nodes who will actually take your stream data and it will work on it, do certain kind of transformation. Then maybe you will want backup processors as well, as we discussed initially, right? So these all can be like backups. Some secondary, some primary backups for some of the servers who are consuming the information from the partitions of a topic. So if let's say C2 is down, so maybe C6 will take over the job, and it will take all the information from 2 and 3, and it will start performing the operation. So it can be like a backup. Okay, the worker nodes can create backup within the same consumer group. And if everyone is actually working, that is good. But then if somebody is down, you have to have some kind of failover strategy for that. So we discussed initially, I think in the first or second class, about 2 failover strategies. About some kind of one strategy was people will be on idle standby, workers will be on idle standby. But this is kind of resource wasted. And another strategy was everyone will be working and everyone will be assigned who is the secondary of another. So if somebody fails, the other workers will actually distribute the load among themselves. If you have watched that video on Memcast, I have also discussed in detail about the thundering herd problem, which can actually arise from this, which is very important to go through. So please go through the Memcast videos which I have shared already. 3 videos have been shared. Okay. So I think this
But
makes sense, and this actually clears out both our problem, that multiple consumers consuming from same partition, or same partition distributing to multiple consumers. Both problems are solved with this, right?
there can be a retry mechanism from the Kafka side, right? When any of the consumer is down,
Read,
there's no acknowledgement coming up.
I think you are saying about retry mechanism
Yeah, that's
for
right.
data transmission.
Correct. Like any consumer that is down,
Yeah,
would ideally not send back an acknowledgement to the Kafka saying, right? So Kafka, we can, I think, configure the retry mechanism strategy and uh, handle
yeah.
it
I
that
mean,
way.
you can do the retry mechanism. Maybe
Mm.
your packet was lost in between. That is completely fine.
Yeah,
But after certain number of retries, that can be configured that maybe I will consider that node to be down, and I will send it to some other backup node.
right.
Okay. So maybe this makes sense now. Why do we actually need the consumer group? Okay.
And I
Now,
also have a follow-up question, Surya. Sorry to break you. So let us say you spoke about bulk writes, right? So it is not only the capacity of Kafka to write in bulk manner, it's also about the consumer to consume that at bulk, right? So consumer should also have the capacity to accept it, right? How do we handle those kind of situations? Right, it's not like just write and leave it, right? We should end of the day ensure that the packet has reached the consumer at bulk. So how do we handle that?
so basically, in TCP, there is a feature of uh, telling what is the window size of writing, or what should be the speed of writing. So you will
Mhm.
say that my speed of writing is, let's say, up to 1 million per second. But it will say that my speed of writing is, 10K per second. Then you will take the streamer will take the minimum of how much it can write and how much the other party can take, and it will it will say that, okay, so let's decide it and fix it at 10K per second. And this is the TCP handshake. Actually, it happens in the TCP handshake in the beginning.
But what if the consumer doesn't want you to write? Instead, he chooses a pull mechanism where, let's
Okay,
say
pull
you're running,
mechanism.
let's say you're running a batch job on a daily basis. End of the day, you want all your jobs to
Hmm.
be pulled at once, right? That's one scenario which we can do through Kafka. So how would we handle that?
So since this is a pub sub model, so
Mhm.
this case, you have to subscribe once and you then say that whatever is available, you just push it to me. So it is not a pull model directly. Because when you subscribe to something and turn on the notification, let's say, then you after that no longer have that control that will you get the information. I mean, I will pull the information. Pulling the information is it is staying somewhere, and when you want, you go and take the information, right? And
Okay.
you have to consciously do it yourself. But in the push model, the Kafka broker will push to the subscribers. So that's why I'm saying that if I don't want notification, I will turn off notification. So I will not know about any information. So it is as good as saying that I will be a non-working consumer in the consumer group. That I don't want anything. But if I when I want to have something, and if there is a conflict in the consumer group, move to a separate consumer group, and then you try to pull your information. So what you are saying about pulling is you will not be pushed your information as per the broker, but you want to pull whenever you want to take the information in, so you will be just idle.
Exactly. So I will pull, for example, daily scheduled. Okay. I will pull only when I need all my events, right? So what will happen is we can, I think, configure, right? In as a subscriber, we would choose a pull model instead of push model. So now comes the case when bulk pulls happen, right? There can be a network issue or there can be a capacity issue in terms of accepting those pulled events. So that's what I was thinking.
Actually, this is not recommended here because Kafka will not maintain your data for a longer time. And maybe the data will also need to be popped off. When you are consuming in a queue, the data will be removed after it has been published to all the subscribers.
Right.
Right. I mean, that makes sense actually.
So
So
that brings me to the third question. The data that is the data or a database in terms of what is there inside the Kafka that is storing the data temporarily, is that a distributed data or it can be a single point of failure to that work to that
no, it can
um,
be distributed. And
mhm.
generally in Google, I have seen GFS systems actually store the data. So there is
Okay.
a separate class on GFS, which will be upcoming, and Google file system that
Mhm.
is actually distributed over hundreds of thousands of databases. So it is like a cluster type database management system, just like your HDFS, if you know.
Got it.
So
Okay.
you cannot assume that it will fail or single point of failure.
Mhm.
You
Okay.
just assume that, like I have used personally Flume. So if Flume is again a batch processing MapReduce pipeline system. Again, we have not discussed MapReduce, which will be coming maybe the next week. So in
Mhm.
this system, actually, you assume that data is coming from one part and you are just throwing it to an abstraction level that I will save it in the DB. So maybe db.save. But then you have no idea about how it is handling on the backend. And you don't have one DB, but you have thousands of DB, hundreds of thousands of DB. So just I made a single DB for that reason. But it is generally either a HDFS or GFS or anything similar, which will actually make the data persistent. It will give you almost 100% guarantee to maintain the data.
And there are chances that
Mm.
uh, there can be some consumers which are at a idle state for a long time. Let us say for a week or two, the consumer has not consumed anything at all. Does a consumer has a life cycle as such?
I mean, then that doesn't make sense to be in the consumer group. It can be on idle standby. if it is not consuming?
Infinitely.
Yeah, it can be. And after some time, if it is idle for too long, you may remove it from the consumer group. But you
Okay.
open the application, that will automatically add you to a consumer group. Like let's say I have personally not used Zomato for 1 year. But if I
Mhm.
open Zomato right now, and if I want to order something online, then I will automatically get added to a consumer group. But from 1 year,
So
I
you
have
will
been
be
removed
tagged
from the.
from an inactive user to an active user, and then you will be added there.
Yeah,
Like,
yeah. So maybe when you have placed the order, until you receive the order, you are in a certain consumer group temporarily for that order update. But once the order has been delivered, then maybe you are only in that consumer group which is about marketing and sales. But you are not in the consumer group which shares live location. You can be present in multiple consumer groups because different consumer groups may be consuming from different topics altogether. Maybe you are always present in the sales and marketing, but you are not present in anything else. But as soon as you place order, you will be placed and you will be removed dynamically. And that is sensible actually, right?
Mm.
So it does auto rebalancing, not just on the partitions, but also on the consumer groups.
Okay.
Okay. So maybe we will require a 10 minutes break. I mean, because this topic is long and uh, it will require a lot more time. What is the time right now? If somebody can tell me in Indian time,
8:30.
8:30. Yeah. Okay. We will require at least 1 hour more, at least, or even more than that. So let me finish this. I mean, this architecture is never finishing. I mean, so let me, since you have asked so many questions, so maybe this is the right time to take a break, 10 minutes break, and let's come after 10 minutes.
If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number.
Let me start. Okay. So I think we had discussed till the consumer. Okay. And you see that if I can just draw an overall diagram. Okay. Let's say a Kafka broker. Again, I will be uh, elaborating the internal diagram again. Like I think Rakshit is like not even visible. So keeping the all those 101 points where you don't have to put light on the back of your head. Otherwise you cannot see. Anyway, so
Yeah, that's a kind of a video. It might disturb others.
okay. Okay. So coming to this point, like let's say there are certain producers. Simply, there are a lot of producers. Then you have the let's say topics, or let's say Kafka broker. So I will write broker. And then you have consumers on the other side, simply using consumer groups. Then the data moves from the producers to broker. The broker has multiple topics. Each topic have multiple partition. All of them have auto balancing and dynamic partitioning. That means you can add or remove partition dynamically. You don't have to do it yourself. It will be done. And then the consumers have consumer groups. They will consume from the broker side. Okay. So this is kind of a pub sub model overall, if I look at it. In the why it is a pub sub model, because the consumers have to first be in a consumer group, and the consumer groups have subscribed to certain topics and certain partitions within the topic to receive the data from them. And if you are present in a consumer group, and if you have subscribed to some partitions and some uncertain topics, then if there is an update or any addition of information there, then you will get it in a stream to yourself. You will get your data feed. Simple. So overall, this is a pub sub model. Okay. And if I can say, the Kafka also behaves like a queue, because in the partition, you can write from one end and it will be consumed from another end. consuming doesn't mean that it will be removed. Like in a queue, consuming means it will be removed. But in this case, it will not be removed. It will be present, but there will be a pointer which will be telling up till which point have we consumed, because these all have to be made persistent in the long-term persistence in the database. So until it is written to the database, it will not be removed. But then there will always be a pointer which will always mention about what is the front of this queue. But that doesn't mean the queue is getting reduced. Okay. So there will be a front and there will be a back. You will always add items from the back. You will always consume from the beginning. You cannot consume at any random point. So it behaves like a queue. So your Kafka behaves like a queue and it works on a pub/sub model. I think this thing should be clear, right? Okay. So let's talk about a broker. I mean, I have already drawn the diagram of a broker. So this is a broker. Actually, this is not a broker. I should say this topic one is a broker. And within a broker, you have one topic and multiple partitions. And you can have multiple such brokers. Like let's say this was a bigger one and let's remove this one. Okay. So then you have another topic, which is topic two, and you have multiple partitions within this topic. And this becomes broker two. And you have a number of brokers here. And this entire thing, lastly, there is a zookeeper, which is used for coordinating all the things that is happening in interaction between the consumer, the Kafka cluster, the topics, the partitions, the producers. Somebody needs to coordinate all these things, and that is the job of zookeeper. We will look at it tomorrow. And the zookeeper is used for coordination of, it is actually a weight-free coordination system. So works it is one of the fastest. So zookeeper is placed, let's say, at the end, and this entire thing together is called Kafka cluster. Kafka cluster. Okay. So this entire thing is Kafka cluster. So I think now you get certain more light into the architecture, right? Now, what is about the, I think, have you understood about the load balancing? Like, okay, I will talk about load balancing. So I'm just keeping it, I mean, I'm just removing this topic for the time being. That is our last topic actually. So it will be in detail. Okay. Now there are, for each of the partitions, the data which is written may not be of the same size, even though it is similar nature of data, but it may be, so certain data can be little longer, certain data can be little shorter. And based on that, all these are written with offset values. Because if you are writing integer value, you have fixed 4-byte size. Let's say you have fixed 4-byte size. But when you are writing this kind of data, you cannot be sure about what will be the size. For certain things, you are 4-byte, but for certain things, you have 8-byte because you have more information loaded there. So for that reason, this partition is actually defined with an offset value. It is not just defined based on index, but with the offset. And since we just read from one end and push from the other end, we don't actually care about it because we are not supporting random access here. So if you are not having random access, it's fine. And let's say the first data size was 10 or maybe 9. Let's say 10. So it was 0 to 9. Next one can be till 14, which was only 5 size. Next one can be till 16. So this was only 2 size. Next one can be 20. So this is 4 size. So like this, it is defined with an offset value. Okay, because data may not be of the same size. What are the messaging guarantees that Kafka provide? So messaging guarantees. Generally, you will find messaging guarantees being required everywhere. Like let's say in the banking system, you will require at least once type of guarantee where you at least is guaranteed to get a message one time. Like let's say you have logged into your net banking and then you want to be notified at least once, but you may get multiple messages that you have logged in. Sometimes it happens, but that is fine with us. At least we should be notified one time because this is important. Missing is not an option. Wherever it is important that the user must know something, then we will go with the at least once guarantee. Something which is not important, maybe some kind of marketing stuff and all, there I will go with at most once guarantee. Because if you are marketing certain things multiple times undesirably to the user, generally marketing messages are undesirable. User will most likely put an effort to unsubscribe. Marketing also has to go with that much of pain which the user can bear, just like the taxation system, right? You cannot take unlimited tax from the people. You have to make certain strategies of tax which is paining to the user, but they are bearing it, right? Right, Lavkush? Okay. Okay. So let's see at most once guarantee. So how do we provide at most once guarantee? Anyone who can answer this? How do we guarantee this at most once, that we should not exceed more than one time? I mean, the answer is simple for this. Just think about, there is a producer and there is a broker. So I'm writing B for broker, P for producer. How can we guarantee I mean, it is at most once. So if you read it carefully, it can be 0 or 1 time. It doesn't say that it is at least once. It is at most once. And there is exactly once guarantee too. Anyone who can answer this? I think you can guess it easily.
We commit the offset and move to the next pointer.
I mean, I didn't clearly get your answer.
We increment the offset so that that message won't be sent again.
That says it is about the live location streaming. So producer sending the live location to the broker, and the broker is required to send it to the consumer. But it can get dropped in the middle due to some network error, let's say. I mean, the answer to this is you just fire and forget about it. You just send the message exactly once. It may get delivered or it may not get delivered, but that will always guarantee that if it is delivered, it will not be delivered more than one time, because you yourself did not publish it more than one time, isn't it? So it is just like it is like a UDP packet transfer, where you do not guarantee the transfer to happen, but you just fire the packet and you forget about it. There will be no retransmissions for that. So simply using UDP will make sense here. Like in the live streaming, you use UDP for this reason, that live streaming timing is very important. If you use TCP there, certain frames which did not come, you will see, I mean, buffering happening, waiting for that frame to come. And after that, all the other frames will come. But actually, we can skip a few frames because it is important to be live rather than maintaining a very high quality and I mean, waiting on each and every frame. Does it make sense? So in this case also, you can use similar kind of option. We will look at live streaming later. Yes, there is 2 or 3 sessions dedicated for that, but it will come later. So you just fire and forget about it. If you lose the packet, you don't deliver it. The broker cannot deliver it to the consumer, or even if the broker gets it, but then the broker may send it to the consumer and it may get lost. So it cannot guarantee to one consumer, but it may be available to another consumer, because the network packet actually got lost when it was sent to consumer 1, but could not, I mean, it was delivered for consumer 2. So maybe certain people will get the message, certain people will not get the message, but I don't care about it. It is fine. Okay. So this is your at most once guarantee, which is the easiest one to answer. Now let's say at least once. What will you answer for this? I think now you can get the answer, right? Any answer for this? At least once.
A retry mechanism?
Yeah, the TCP retransmissions. Simple. You can apply TCP retransmission and it always guarantee that you at least send it once. You keep on trying. You can set a limit to how many times you try, but you keep on trying. If there is a failure, you again retry after the timeout. If there is again a failure, you retry, and there will be an acknowledgement to the to whoever is sending using the TCP connection. So I think somebody asked previously about acknowledgements, but acknowledgements are not always necessary. If you are transmitting, which is with the guarantee of at least once, you will need that TCP acknowledgement. But if you are sending with at most once guarantee, then you don't need the acknowledgement feature.
Don't you
Okay.
think Arc ID is required to remove the data from Kafka storage until we get an acknowledgement back that it is delivered?
No,
Technically,
so that is essential only with the database.
Mhm.
Because if we want to remove something, I want to make it persistent somewhere. So it is just a feature between the database and the Kafka. So that is handled separately than the other consumers. So database is separate. It is not in any consumer group, but the Kafka has to write the data to the database. And when it has to do that, that is separate stuff. It cannot remove the data unless it has written to the database. And it can also not remove unless it has published the data to everybody. The higher of
Right.
these two types is taken.
So what happens is any event that comes, first thing the publisher does is to actually write the data in the database, even before consumer can consume it, right? Right. So that being the case, what is
No. I mean, it may not write because you see, there is a real-time requirement. And if you are waiting for it to be written to the database, maybe you are not transmitting the data real time to the services or the consumers. I mean,
So you're
all
saying
the
in
more
not all
reason why we
cases it is
removed
going
that.
to store the data, but in only certain cases.
I didn't get your initial
So
sentence.
you're saying that only in certain cases, Kafka is going to store the message in its database, and in certain cases, it just directly tries to transmit the information.
I
That's what you're saying.
see the where is the figure? So broker will write to the database. This is separate from the consumer set. Okay.
Okay.
Now, and the transmission from the broker to the consumer is a separate thing. Now, why did we move away from database and come to the Kafka cluster? Because we could not afford to write the data to the database and query from the database, because writing was very difficult to the database in real time. It could lead to crashes. So that's why we added the cluster. So if you think that's why we added the Kafka cluster, then why will we wait for data to be written to the database, right?
Okay.
Right. I mean, if we were waiting to be written to the database, then why don't we use the database directly? Because
No, there are
it
two
can.
databases here, right? So one is Kafka internal storage database. The
Yeah.
other is the permanent storage, which I think you're
I
talking
mean,
about.
definitely it will first write in its own storage. Those are
Ah,
the partitions. So partitions
right.
will first save the data, whatever it is receiving, and then only it will publish to the consumer. Okay, I think I am
So
confused. I was
yes.
confused about this database actually. Yeah,
So my
definitely it has to
question is,
save. Yeah.
yes. So
Uh,
it needs a written acknowledgement. Arc ID should be acknowledgement ID should come back. Only then from the partition it will remove, right?
I mean, to whom are we sending the acknowledgement? To the Kafka itself, are you saying?
To the Kafka itself.
Yeah. Those all will be its internal management. So those are the job of the zookeeper. Whatever
Right.
happens in the Kafka cluster, that zookeeper handles. Data is
Mhm.
coming, when it is written, when it is ready to be transmitted, those all things are taken care. But it writes very fast, makes the writes happens very fast, and writes a large number of writes parallelly. So, so that's why we use that simply. So yeah, that is the job of the zookeeper, to manage when it is ready for transmission. But it will make it happen very fast in real time. Okay.
Mhm.
Yeah, definitely that has to happen. If it doesn't write, it has to make it persistent. If it is not persistent, maybe you will lose the data and you have also transmitted it. I think someone else is asking something. Purnima, are you asking something? Where is she? Okay, she has left maybe. Okay, so yeah, coming back to our point, at least once guarantee, I think it is clear, right? So you can say at most once guarantee. Simple UDP protocol works in similar way. I'm not saying that you use the UDP. TCP/IP works similar to your at least once guarantee. Then there is exactly once guarantee. How do you provide this? And this is not just limited to your Kafka, by the way. These all applications are present in all the other designs. So I'm just discussing it at one place because you can apply it at multiple places, right? Messaging system and anything like that. So exactly once guarantee, how do we do that? Any idea you can make out? Exactly once is, if you think about how to identify that certain thing was already given to me, then I will think about who is sending the message and what message it is being sent. If I know these two things, then I will know that this I have already seen. So maybe if you can identify something with the ID, message ID, let's say message ID, and with the user ID as well, with the producer ID, I will say producer ID and the message ID, because two different producers can produce the exact same data at two different time, and you will think I have already seen it. That is not the case. Okay, the user ID should be same, the message ID should also be same, and the message ID should be monotonically increasing for every user. Monotonically increasing, strictly increasing value. So when you send a message, with ID, let's say 5, the next message must go with ID 6, next message must go with ID 7. Okay, maybe timestamp would be a good approach there, but again we have that problem of time skews and time readjustment, where you are moving ahead in time and suddenly you sync with the NTP server and your time moves back, and again you start producing the same sequence IDs, and then the Kafka will think that you have already given this message, so I will not listen to it. So maybe time is not a good way to do it. Maybe you will use a monotonic counter yourself and make it persistent, so that if you crash and next time you come up, you don't restart from zero. Okay, maybe you can handle that. So exactly one's guarantee is all about idempotency, and idempotency can be achieved if you can make out that certain thing has already been seen, and that can only be done if you are following some kind of sequence ID or message ID which is monotonically increasing, and producer ID as well, who has produced it. Are we clear? So with this, I think you should be able to do it.
So
Okay.
I didn't understand what is idempotency. Can you please elaborate?
Which one? Message ID?
What is the meaning of idempotency and
So idempotency in simple terms, if I say that you have a matrix M and you want to get a matrix M as answer, what will you multiply it with so that you get the same matrix? This matrix is called idempotent matrix. Similarly, if you have any integer number, let's say 50, you want to get an answer 50. What value should you add here? Idempotent value, that you get the same value even after any number of operations. So that's value 0. Depending on the operator, the idempotent value will change. If you want 50 again, this will be 1 year. If you have M and if you always want answer as 1, then you will always multiply with M inverse, which is 1 by M simply. So it is about if you apply the same operation multiple times, the state transition happens so exactly one time, but no more than one time. So let's say there is in a state machine or in a finite automata, right? So DFA or NFA, whatever. In this case, if you have multiple states S1 and S2, then there will be a transition from state S1 to S2 on seeing something. Let's say on seeing all the smaller case letter from A to Z any number of times, you can move from state 1 to state 2. But for transition to happen from state 2, you will have to see anything from 0 to 9. Just giving a separate example, right? So in this case at state 2, if you again see A to Z, it will not do state transitions. And you can apply it any number of time, but it will only go one time from state 1 to state 2, isn't it? Right? All these are idempotent operations.
This is more restricted towards a single topic, right? Like it's more like a single topic partition you're talking. So does this provide a transactional guarantee, right?
Oh, exactly once.
Yes.
Yeah. So you can use TCP IP with the idempotency. So even if you lose the packet, you are sending it, and once you deliver it exactly once, you will get the acknowledgement. Even if the acknowledgement is lost and you are again retrying, okay, if the acknowledgement is lost, still the broker is forwarding after getting the message. But if you send it again, it will either ignore it or it will send it back that I've already seen this message. Right? I've already seen this message. So an acknowledgement can be sent. So this can be used with TCP/IP.
Okay.
With
And
just a
this can
session
happen
management.
across partitions.
Yeah, this will,
Okay.
this will happen
Like,
across partitions.
like what will happen is there can be multiple producer sessions that would be handling these ID potency cases, right? So won't there be any kind of issues in that?
Okay, you are
Right?
saying about conflicts that won't
Exactly.
there be exactly two unique IDs or
Yes.
whatever
So
we
there is
have.
no guarantee that it's running in the single server. It can be running across
Yeah.
in
It's
the
completely
different
fine.
regions also.
Yeah, it's it's completely fine. So that's why, I mean, why do I want idempotency? I just want it on a single message and
Correct.
it is separate from a second message. Every single message is separate. So I just want it on a single message. Every single message has a different MID. That is message. Okay. And a PID says about which producer it is getting produced from. So if I have this information and if I also maintaining persistence on monotonically increasing MIDs, so that even if that any crash happens, still you will restart from wherever you had left. If I had left at 5, I will start at 6. Okay. So in that case, every message can be uniquely identified, isn't it?
Right.
The only way where it would be duplicate on different messages and would create a conflict is if you are not maintaining persistence in the monotonically increasing value, because producer ID is same, right?
And another question, like let us say I mean, basically the whole point of this is like first in, first out, right? There should be some sequence ID which kind of maintains the sequence of all the incoming messages, right? So if this is happening in a distributed system, right? So how will Zookeeper actually manage these sequences across different partitions, right? Like let's say in one partition you want something to happen before the next partition takes up, right?
Yeah.
So how would that actually happen? I'm just
Okay.
curious.
So I think you are asking about how if the messages are sent to different Kafka clusters, stream
Exactly.
to different Kafka cluster, then how it will manage it. In
Yeah,
most of
let's
the use
assume
cases,
across regions, right? So
okay.
let's make it as complicated as possible.
Yeah, across region. Okay. First, let's solve it in an easier way. Most of the applications that you will see which has a real-time requirement as a local requirement. First thing, whatever we discussed, everything has local requirement. If anything has a global aggregation thing, then that is actually an analytics problem which is handled with the data warehouses, not with the Kafka stream. Okay, that is another thing. Then if you are saying that if it is required, generally Kafka we use for smaller regions. We don't use it for a very large scale, I mean, distributed system, which is like for the entire Asia Pacific region, I will use a single Kafka cluster. Generally, we don't do that. But if we do that, let's say we are using this in a data center, and if we are sending messages from different regions into the same cluster, we will be sending it to the same cluster. Actually, your question, I think, is assuming that we will be sending the message to different Kafka clusters.
Correct. Correct.
Right. So even if I assume a Kafka cluster being in a single region, actually, I don't think about a use case, which is real-time use case, that you will be watching the cab driver from US. Generally, the application itself will not allow you to do that because you are not present in the region. Because they don't want to handle such complexities. Simple. And actually it doesn't make sense because the cost you will incur will not actually justify the use case. Like who would want to track a cab in Seattle from Bangalore? It doesn't make sense. So they will not even allow you to do that. And they will always track your location and will show all the outlets in your location unless you force that no, I want to order from Delhi, not from here. So I want to order for my friend in Delhi from Swiggy, but not in Bangalore. And then you forcefully do that. But then again, it becomes local because you cannot be ordering something from Delhi to here on a real-time basis, Delhi to Bangalore.
Correct.
It is too far away. So I will assume that all the updates for the real-time things are going to the same Kafka cluster, because one region generally doesn't affect in real time with another user. Like if I'm thinking about a match, a soccer match, let's say, then I will want the weather information of that area, right? I will not want of any other area or something like that. I will not want to aggregate weather in US with weather in France, weather in India, and all those things aggregation. I will try to avoid that. If you want to do that, that is a different analytics problem. That doesn't have real-time requirement. You can do that on the back end with the
Yeah,
with
right. Like if you're doing something with BigQuery or
yeah, yeah.
something.
So that is separate, right?
Yeah.
So here we are more concerned about tracking the real-time things, which is not having a huge data build up. It is a small data transfer, but it needs to be transferred fast and in real time, right? Right. So I think most applications, as far as I know, they try to avoid this problem, whatever problem you put forward, isn't it?
Yeah, it makes sense.
Isn't it? I mean, they try to avoid that because it is not financially feasible, actually. It doesn't make
Yeah.
sense for them.
Yeah, they're basically paying a lot for something that is not required.
Yeah. So I will also want to avoid this thing, isn't it?
Mhm. Yeah.
So let's see. I hope Lavkush is not sleeping, right? Are you getting the question, Lavkush?
Yeah, yeah.
Okay. I will not discuss about the isolation levels because we have already discussed that. So you can, if you have not read about it, I think you can read about the isolation levels, read uncommitted, read committed. And I think we have already covered that in the HRD basics. Okay, so isolation levels, why we require certain level, what level should be maintained. Different options are also available here. You have to decide on what isolation level I have to decide. So those all things already covered in the HLD basics. So not covering here again. So let me make a simple transaction flow where how the Kafka actually make a transaction is shown. So let's make a transactional client. So there is a client which helps in making all of the transactions. Then there are multiple transaction coordinators. Transaction coordinators. Okay. So since there are multiple coordinators, generally we draw like this to show that there are multiple coordinators. Then we have multiple brokers. So, and all the brokers together form a Kafka cluster. So let's say there are multiple brokers. Now, what happens is when a transaction has to happen, it goes through a transaction client. Transaction client doesn't take care of the entire transaction, but it just connects you to a transaction coordinator and the broker. So the broker is responsible for the data transfer. The transaction coordinator is responsible for where are we in the transaction and how to handle the transaction. Are we taking some logs? What are we doing? So that is the job of transaction coordinator. Okay. So let me give you an example of one of the transactions. So let's say we want to initiate the transaction. So there will be an I need transaction request. Let me send the I need transaction request to the transaction coordinator. So this is number one, which is, let's say, I need transaction. Okay. So whenever we want to initiate a transaction, I have to say to the transaction coordinator that I want to initiate something. The broker is more interested in the data, not in coordinating the things. Coordinator will have to do the management job. Okay. So here there will be a coordinator log where if something happens or something bad happens, we can do postmortem. We can see what all had happened and where did we actually get stuck or anything like that. If you want to manage all these things, so it will write that there is a request for init. So it will say init request on a transaction with an ID. What is the transaction and what is the ID of the transaction? Simple. So it has updated. Now the second request will be about actually doing the transaction. So let's say the second transaction is coming here and I'm writing 2,1. That is, this is the second message, which is about actually performing the transaction. So it will set the transaction status to transaction ongoing. So let's say I'm going transaction.id. So let's say transaction.id is ongoing. So I'm writing here ongoing. Okay. Transaction is ongoing. So this is when the transaction client says to do the transaction. Fine. Now what happens is when this is set, this is 2,1. When the status is set that the transaction is ongoing, then the transaction will start and the actual messages will start streaming to the broker. So I can write it as 2,2. This comes after you have set the flag of transaction is ongoing now. So in this stage, the production of messages from the producer goes to the broker. Producers on the left side of the broker, then you have brokers on one side and consumers on the other side. So producers messages will be streamed to the broker, and even if there are some commit messages and all, commit about whatever, it will be sent to the broker to do the same job. So let's start with the producing messages. Now once you have started producing the messages, then again you have to maintain two separate parts for it. One part will actually write what data are you actually writing. Another part will maintain the log about what is the status of all the things that you are doing. So let's say one message comes, which is 2,2 about production of a message. And let's say message M1 has actually come and it is written here. Okay. So this is your actual partition. I will write it as partition. Let's say. So the broker is writing the messages to the partition. Along with that, side by side, it will also write to the consumer offset log, and it will say that where it is written, that is written in the log. So let's say transaction, whatever number or transaction ID, it will be written, and some kind of offset will be written. Let's say offset X or something. So where it is written, all the metadata is written in the consumer offset log, and the actual messages are written in the partition. Metadata is maintained separately. Okay, so this is 2.2. Are we clear till this part? Are we clear? So at this point of time, your message is written. If again a message comes, then what will happen? If again a message comes, then message M2 will be written, and it's another TP1 whatever ID, and then offset Y is written. So at some offset, this thing was written, right? So like that, it will keep on updating. So I can keep on updating this as long as we want to write it, it will keep on updating. Let's say that after doing the transaction, we want to do commit or abort simply. So that will come from the client side, that we have to commit or we have to abort. So let's say this is message number 3,1. So I'm separating different type of messages. Init message first, then about producing and consuming all kind of messages. First we save the messages, and the third type is do either commit or abort. So in this case, when you have to commit, I hope you have attended the session on atomicity. So I have already uploaded the video if you haven't. So there we have talked about two-phase commit, three-phase commit, and then about quorum commits, leaderless, and everything we have discussed there. So please watch that. In this case, it uses the Kafka uses two-phase commit. In the two-phase commit, what happens is there is a prepare phase. So the client is asking, the server is asking the clients to be prepared to commit, and then everyone has to answer, okay, I'm prepared. And once it gets all the okay messages from other side, then it will say that okay, now everybody is ready, so you commit, and then again an acknowledgement can, okay, we have committed. Simply. To read more and more complexities about what are the pros and cons and what are the problems, you can just read about it from our atomicity class. Okay, so we are not discussing this in detail. So there is a prepare phase. That's what I want to say. So it will say that on the transaction ID, TID, we are entering the prepare phase. Okay, so in the prepare phase, what happens is the coordinator will ask everybody to be prepared. I will send you the commit. I mean, are you guys prepared to commit? That's what the coordinator will ask all the partitions or all the brokers, let's say, wherever it is going, right? So then it has to ask the question. So this is 3.1. Okay. Are we clear till this part? Are we clear till this part?
Yeah.
Okay. Now, once the coordinator has actually saved it in the coordinator log, let me just write it, coordinator log. Once it has saved it here, then it will pass on the message to the broker as, let's say, 3,3. This is the third message which is going, and it will say either you write the commit or abort marker. I have discussed about this marker in the memcache class, so please look at that. Okay, so there is a detailed explanation of how the markers work. So the coordinator will tell the broker that, okay, you need to either commit or abort. Let's go with the commit. Okay, so you need to commit. Then after this, the broker will be sending the message on the offset side, and it will say that, okay, I mean, I don't have space there, so maybe I will write it here. Okay, I mean, it is just the continuation. So it will say that TID needs to commit or abort, whatever. So let's go with commit. TID will be committed. This is the consumer offset. Are we clear? And then in the partition also, if you want to write, if it makes sense, you can write TID commit. I'm writing C with the commit that it is being committed. So when something is committed, then you are ready to transmit it. When something is, I mean, you have been writing the messages to your local database when it is coming in the Kafka. And once the commit has been done, then only you make it eligible to actually stream it outside to the subscribers. So this commit has to happen. Okay, so and like this, all the other messages will also work. So I'm writing it 3,4. So this is just a single flow. So I'll write this is the data, and again these partitions belong to the topics. So there will be multiple topics. Okay, and this is just in one of the topics, one of the partition. I have just zooming it out here. This is just one of the partition, and there will be multiple partitions within a topic, and there will be multiple topics. So this is just a single partition of a single topic, which is zoomed out here. And then this is what consumer offset log. And on the left side, you have the coordinator log. So coordination job is done by the zookeeper. And then this is the consumer offset log written on the other side. And I think, is this making sense now? Like how a single transaction actually goes through. So two PC is used in the initial Kafka design, two PCs.
This transaction coordination is happening at zookeeper side.
Huh?
This transaction coordinator, this is placed
Kafka cluster. These all are in the Kafka cluster.
Yeah.
These are not on the producer side. Everything is happening on the Kafka cluster. The zookeeper is also present on the Kafka cluster. The metadata is also maintained in the Kafka cluster. Partitions are also in the Kafka cluster. Okay. Are we good here?
So if there are multiple clusters, there will be multiple instances of zookeeper also.
Yeah, but the cluster is quite large.
Yeah. Cluster is
Quite
large.
Yeah. So can we go to the next part? I think so. So this is about each transaction, and this is being repeated multiple number of times. Okay. So let's go to the next part. I'm not sitting with my clock, so I'm not able to track time. And I don't know if I'm see. So I think I'm going slow, isn't it? Are you guys able to get it, or should I go faster? What do you think? What is your take on this?
It's right.
Huh?
It's
Right.
right.
Faster. Rakshit
No.
is saying faster.
No, this is a good pace.
Yeah.
Okay. Okay, fine. You see, this time I have added extra topic. Like last time also I have covered Kafka, but last time and this time is different. Last time I had covered it in 1.5 hours. This time I have added load balancing as extra topic. We have not even started load balancing. Anyway, going to the next topic. How how do the data is maintained within a single partition, and how it is made persistent, right? And what can be the conditions for data loss from within a partition. Like I cannot say it is 100%, no, you cannot lose the data. Even in any kind of database, you can lose data. You can provide 99 point some percentage, but you cannot say 100%. So there should be certain scenarios where you may be losing the data, right? So let's see it here. How do we maintain this guarantee of data, that I will not lose data, and when can you lose data actually, right? When can you lose data? Like let's say you and your replicas all are down, crashed forever, then you will lose the data for sure. Whatever number of replicas you manage, all the replicas can go down and you can lose the data forever. It will never be recovered. Generally for that we maintain, if we have attended the storage retrieval, we maintain the LSM trees. In the LSM trees, we write the logs of each of the operation separately, and that has a different replication altogether, which is independent of the database. And whenever certain operation is coming, we first write it to the write ahead log using the LSM trees, which has its own cluster of managing the persistent logs. Once it has written, then only the transaction goes through, and then acknowledgement comes to the write ahead log and also goes to the whoever is performing, like the client. Okay, so that gives more persistence to the database. Even if all the replicas and all the databases are down, still you can go to the logs one by one, and you can start from a state, initial state, and you can go top down. I had also given you homework on reading how to take consistent snapshot using Lampport's snapshot algorithm. I hope you have noted it down, right? It was given in certain class. I think logical clocks and some class, in the clocks class. So please also go through that. Okay. I mean, those are too much detailed. Nobody's going to ask you all these things, but it will give you like more understanding in the topics. Okay, so let's go to a new topic about data loss management. And the topic name is in-sync replicas. And I don't want to use this name, so I will use ISR, in-sync replicas. Okay, what is in-sync replica? Now, when you are writing something to the database, right? So in the quorum management, you might have seen that there are multiple nodes which are available. So let's say I will say DB1 node, DB2 node, DB3, and let's say DB4. Let's say there are 4 nodes. Okay. Now, if there is a main master node, and let's say that master node is DB0 is the master node. Anyone can be master node. Let's assume that all the databases are similar. So I cannot say that the master is more efficient and others are less efficient. Not like that. But if it is so happening that you are making all the writes to the masters and all the reads from the slaves, like all the other databases are slaves. So you are writing to the DB0. Okay. And by the way, I have also discussed about hybrid structures in the memcached, in the distributed caching, how a single master multiple slave architecture is maintained in a hybrid version where the reads are also happening from where you have written, like DB0 sometimes, and why that sometimes, in what conditions do that happen. So please go through that. Okay, I mean, that is, I think, very detailed discussion which covers a lot of topics. Okay, so anyway, I am making write to DB0 and I'm making read from the other topics. Now, if you want to maintain certain other candidates to be leader, like if the leader is down, there will be election. We already saw the raft algorithm of how the elections happen in a distributed environment. If DB0 goes down, election will happen. But there are multiple other simpler ways than raft. Raft is not always preferred. There is a simpler way that I will always say that the vice principal will become the principal if I am removed or something happens to me. So it is already standing as a backup. The vice chancellor becomes the chancellor if the chancellor is removed or something happens to him. The vice president becomes the president, right? So the secondary leader is already selected, who is maybe equally capable enough to take the job. And this will actually remove all kind of headaches for me. do a re-election, choose a new president and all these things, right? For the time being, there can be an interim president, which is who is the vice president simply, if the president is unavailable, right? Simple. So in that way, I would not want just anyone to become a leader just because he got the votes. It cannot happen. Like, let's say, using the raft algorithm, I hope you remember the raft. In the raft leader election, what happened was, if the DB0 went down, let's say, then everyone will start with their election timeout, right? And then everyone will, whoever's election timeout is ending first, will actually ask for votes from the others. And the others will have to vote if they are requested the first time. They have to vote. They cannot say, I will not vote for you. Only from the second time and onwards, they cannot vote. How many of you have attended the raft? I hope you have attended, right? So there was a good visualization. And just go through that website. Okay. So in that case, let's say that DB0 had 5 updates, 1, 2, 3, 4, 5. This was about DB0. But then DB1 and DB2 has the exact same number of updates, which is still 5. But let's say DB3 and DB4. DB3 has only till 3 updates, and DB2 has only till 2 updates. This is 1, 2, 3, and this is just 1, 2. Now, it so happened that since the election timeout is selected at random from 150 ms to 300 ms, that was mentioned in the raft, if you remember, 150 ms to 300 ms. Let's say that it so happened that the random number assigned to DB3 was less. And so DB3 won the election. And so it will declare itself to become the leader. And then it will start writing from the 4th offset. And that's why these all will be invalidated. Don't you think? It will be lost forever. So the more out of sync you are, the more data loss will happen for you. This is one very common case of data loss, where if you are not very sure about what algorithm you are using for leader election, you will have consistent data loss. And depending on what service you are applying this logic to, it can be very costly for you. Isn't
But
it?
ideally, Kafka make sure that these things won't happen, right? They
No,
are like
I'm not saying that this is in Kafka. I'm evolving the problem. Okay. Kafka doesn't use this. I'm just evolving the problem. Okay. Because once you know the problem, then you will more appreciate about the solution, right? If I directly say the solution, maybe you will not appreciate that much, right? Kafka doesn't go like this, but I'm just saying that if you happen to use like this, then what would go wrong? So I'm just saying that you cannot just blindly apply any algorithm. Since you know Raft, you are just consistently applying Raft everywhere is not useful. And there are other algorithms for different scenarios, just like there are different sorting algorithms for different data type of sorting, different scenarios where they perform best. Like this, you have different scenarios where different type of leader election algorithms will work best. In this case, what I would want is whoever I would always want the leader from database 1 or database 2. I would not want to consider 3 or 4. This is 4, right? I will not want to consider 3 and 4 because I don't want data loss. And even if none of them are updated, but I will want the least data loss to happen if I cannot avoid anything. So there is a concept called in-sync replicas, and these are actually the most updated databases group, which are updated with the master. In this case, the ISR group will form with, let's say, database 1 and database 2. So these are generally the high performing worker nodes who are actually as close as possible, almost with the least latency. It is the most updated databases group. Then if any leader election has to happen, whatever algorithm you use, either you use Raft or you use whatever, but you have to consider the ISR group, and you can only make from the ISR group. Like how if a prime minister has to be selected, the next prime minister from a different party because something happened to the prime minister, It will always be the cabinet of ministers from where it will be selected, not from the non-ministry MPs. It makes sense, right? It makes sense. So this is that kind of level. ISR group is the most updated, hence it will give you the least data loss. Are we clear in this? So Kafka uses this ISR strategy where it says that I will always try to maintain some few the fastest of worker nodes, maybe the least loaded as well, who knows. But then it will be highly probable that it will always be updated. And so whenever the shift has to happen, then I know from which group I have to select a leader. So this will guarantee least data loss or least to no data loss even. Maybe some of the worker nodes may be intentionally given low low load so that they can always be updated. So they focus more on the updates because they are acting like a backup leader. So those will be in the ISR group. Now, are we clear what is ISR group? I think so. Right. Then on a separate note, I'll come back to this ISR group. On a separate note, I'm saying that whenever you are writing the data, okay, you will continuously keep on writing the data. Let's say you are writing the data from one end, okay, you are continuously writing the data. Then if you have written the data till this point, then this is called log and offset. But then as you write the data, it may not be acknowledged by the Kafka right away. I think Rakshit already mentioned that you cannot just write it and stream it right away. There has to be some delay into saving the data into its local database. And that is correct. You have to save it in your local database. And only when the local Kafka database says that it has been saved and made persistent, then only from there you can publish. You cannot publish from right away from where you have written the last update. No. So this is called a high watermark. I mean, this is just a technical term. You may not remember all these things. But the thing is, till this point, it has been acknowledged, or I will say it has been acted. Until this point, it has the data has been written. But you cannot take the data in between and stream it all together. You have to only take from the act data. But it happens very fast. Writing is also happening fast, right? So just I wanted to mention because there was a question here right in the past. Okay. So it has to be act by the this thing, by the Kafka cluster. Coming back to your ISR, leader election should always happen from ISR. Let's say that at some point of time, some of the databases gets loaded or it behaves in an unwanted way or it lags behind even more. So if a database is lagging behind more, it will be removed from the ISR cluster and some other database may be prepared to move to ISR. But the ISR group is dynamic in size. It can increase or decrease. It can increase or decrease. Okay. If certain nodes is not behaving well, if it is not fit to be in the ISR, maybe I have set a criteria in ISR that no more than 2 writes delay can be there. No more than 2 writes delay. Database 2 was working fine, but after at a certain time, it saw that it has 4 or 5 writes delay. Then it will be immediately removed from the ISR cluster. You can maintain different level of warning, maybe a soft limit and a hard limit. A soft limit is for warning and tracking the database that this may have to go out. It's not healthy. And then suddenly you hit a hard limit where you have to remove that guy. Okay. So I think the management strategy is clear, but what is the use of ISR and what will be how many losses can it actually handle? Okay. Right. Using the ISR set, let's say that if the ISR set has n by 2 items, out of the total n databases, if n by 2 databases are in the ISR, n by 2 databases are in the ISR, then how many database losses can it actually take? Who will answer this? Like let's say 4 databases are here.
Can you repeat the question?
Okay, let me simplify the question. So let's say there are 4 databases. I'm not counting the master, current master. So there are 4 databases. One is master, that's separate. Other than that, there are 4 databases. Out of 4 databases, 2 databases are in the ISR. Now I'm asking you about if 2 databases are in ISR out of 4, then if at random your databases can crash, I mean the master can crash or any number of databases can crash. Let's say I want to select a new master and suddenly multiple database crashes happen. Then what is the chance of correctness? How many database losses can I handle and still be up to date? Still guarantee that a new master which is selected will always be up to date. Like let me put in another example. Let's say that if database 3 is crashing, and I am in need of selecting a new leader, can I guarantee that I will be selecting somebody who is up to date? Yes, I can tolerate the failure of DB3 because I can select anything from the ISR. Again, on another note, if DB2 fails from the ISR, can I guarantee that I can select somebody who is up to date? Yes, I can select DB1, right? Who is also in the ISR. So I'm asking about how many DB failures in the worst case scenario can you tolerate in this case, and you can always select an up to date leader. I hope my question is clear, right? So my back is paining. To stand up a little bit. Yeah. How many?
Maybe the number of databases are part of in-sync replicas.
So
Yeah.
is it not n by 3?
Yeah, I think Lavkush answered it correctly. So in the worst case scenario, what will happen is all the losses will happen from the ISR group. I'm thinking about the worst case scenario, right? So all the losses may happen from the ISR group. And if all the losses can happen from the ISR group, then I cannot get any up-to-date guarantee of a new leader. So how many I can tolerate is always ISR size -1 because I need one node to be chosen as leader. So how many I can tolerate here? Only one database loss I can tolerate. Because in the worst case, why will my DB4 go down? My DB2 will go down. And in the next attempt, my DB1 will go down, right? Okay, so considering the worst case scenario, I will always be able to tolerate ISR -1 number of nodes failure. Now, depending on that, how will my availability be affected? Let's say not availability. Let's first talk about the durability. Durability is if you are saying something is persistent, it is better available. It is better saved somewhere, right? You should not consider any kind of losses here. So durability will be higher if your ISR size of the group is higher, isn't it? Because if the ISR group size is higher, then you can tolerate more failure of the nodes. But if the ISR size is higher, then what about the other factors? What about the factors like performance? Maybe the performance would require acknowledgement from the ISR group that have you written? What strategy should the DB0 here the current master should use for writing? Maybe if it wants certain backup, then maybe it will say that I will use a quorum approach where the ISR must always acknowledge to me that yes, I have updated. And so I will send that, okay, your update is done. But if I want to tolerate more data loss, then maybe only DB0 and one of the ISR, any item from ISR group, there you can maintain a quorum in the ISR group as well, that if half or majority of the items from ISR group say yes, then I will say yes. You can go with any possible strategy you have, but the less number of acknowledgements you get, the more chances of data loss you get. Right? Simple. So durability will be higher with the ISR size. I hope we are clear, right? So I think I don't need to discuss on this right now. I think now you can make out about the availability. Performance will depend on how many acts you require. More X required means less performance. Okay. So if you have ISR size 1, you have the least durability but the highest performance. If the ISR size includes the entire all the databases, then you will have the least performance, but you have the highest durability. Right. I think now you can make out the trade-off, isn't it? So let me give you certain diagrams, since HLD doesn't end with diagram. I mean, it doesn't end until you draw a diagram, isn't it? Like, what are we even discussing if you haven't made a diagram? So let's make a simple Kafka cluster. So let's say this is your Kafka cluster. Kafka, just giving you an overview of what we have covered till now. Then we will go to the load balancing. So in the Kafka cluster, you have broker one, and within a broker, even within the broker, you can have multiple topics, but I'm just writing one topic per broker. So this is one broker, let's say. And then you have topic one here. So let me change the color for this. So topic one. Even in this case, you can have multiple topics per broker, but let's consider one topic. You can have multiple partitions here, and number of partitions. Okay, so this is broker one. Within broker one, you have topic one. So I'll just encircle this topic one with another color. Since you can have multiple topics per broker and you can have multiple partitions per topic. Okay, so this entire thing together is Kafka cluster. Below, you can have metadata about everything and coordinator, which is zookeeper. So you have producer on one side. You have consumer on the other side. So this is streaming the messages. So maybe writing the messages. Then it is also being tracked by the zookeeper. The zookeeper is also tracking the consumers, maintaining the consumer groups and all. Who does this? The zookeeper does all these things, maintaining consumer groups. Who will be entering the consumer group? Who will be leaving? Anything about coordinator? It is the zookeeper who is doing this. So consumer message. Okay. And the zookeeper gets the Kafka broker ID. Where is this producer streaming to? Which broker is it streaming to? The zookeeper keeps track of that. Then we have seen in the transaction how a single transaction happens, right? So the zookeeper actually is the coordinator there, and it is doing all kind of transactions and writing the log. So update the offset value. I'm just writing offset value, but if you look at the diagram, this is performed by the zookeeper. Okay. The broker is one side. A broker is not the zookeeper. The partition and all are not zookeeper. These are all the database spaces where it is written. Storage space, broker is different. Broker contains topics. Each topic contain partitions. Consumer offset log is different. Coordinator log is again storage. Transaction coordination, everything about how the transaction happens is handled by the zookeeper. Okay. And this entire thing is the Kafka cluster. And this is your Kafka architecture. I'm not writing different brokers. It will just be replicated, right? I hope you know it. So are we clear here on a high level? But generally we make Kafka like this, like a pipeline, where you get data from one end and you remove data from the other, and you just publish the data from the other end to the subscribers. So let's make another diagram based on that. So you have producers who are producing the data, and it is going to the Kafka cluster. So we have already seen how the Kafka cluster looks like. And let's say this is the Kafka cluster. All this combined into a single pipe. Okay. So the messages are going here. So these are the write messages, which we have seen here, the write messages. Okay. Then there will be certain set of consumer groups here. So I will write their consumers, and all the data are being streamed to the consumer. So consumer messages. Fine. Then there will be DB, which I have not made in the last diagram. There will be a DB where the Kafka it is the DB where the Kafka is making the data persistent. We did not want to write directly to the DB, but then Kafka cannot hold it for a very long period. Okay, so bulk writes to DB. Bulk writes to DB is happening here in the DB. And then there will be stream processors on the top. So Kafka is used for event-driven systems, stream processing, real-time feature monitoring, and all those kind of operations. So we will have stream processors because Kafka in itself is not containing processors, but you will need some worker nodes who will actually process your data if you need some kind of transformation or anything. Then the Kafka will work in tandem with the stream processors. Okay, so this will do your data processing and transformation, just like your ETL. Okay, so this is also Kafka architecture, you can say. Kafka architecture. I think this makes more sense than the previous one. But in here, the Kafka cluster is not visible. Here, the Kafka cluster is visible with the zookeeper and the metadata somewhere here. Metadata being held by the zookeeper. So I'm not writing the metadata. Okay, are we clear? So, oh, sorry. So I think we are now moving to the last topic, which is the load balancing, which I have added new to this patch, which is how to do load balancing in Apache Kafka. But where do we need load balancing, by the way? Let's take an example like load balancing in case of GoMMT, Make My Trip, or any online booking system, Agoda, or let's say Airbnb, or any kind of whatever, hotel booking system, flight booking system, cab booking system, anything, any such application will require Kafka and will require load balancing because they have huge information transfer happening. So if we take an example, they have daily transfer of 100 of TBs of data, daily streaming of this much amount of data that they are doing. So definitely we are not working with the small set of data, it is huge set of data. And so how are we managing the nodes is extremely important. We don't want to overload certain node and make it crash or underperform while others are just chilling around, not even working. We want to be as fair as possible in the allocation of the jobs. Okay, but how will that fairness come? Can somebody tell me like, okay, I mean, can somebody tell me like, how do you become fair in assignment of work? Where is that assignment diagram? Yeah, this is the assignment diagram, right? Or let me make a new diagram altogether. So let's say that there is a Kafka distributor inside the Kafka cluster. Or let's say there is a consumer, producer, whatever. So let me make a simple diagram. Consumer. In the Kafka cluster, there is a consumer who consumes the incoming messages. Okay, consumes the incoming messages. Then there is a producer. After consuming the messages, there will be some transformation on the message if required using the stream processors inside the Kafka cluster. First, there will be a consumer who will actually consume these messages. Then it will connect to the stream processors if it requires certain data transformation or you have written some data pipeline where some things will happen. You connect. If you don't want to do something, you just stream it as it is. So there will be consumers who does that. After consuming, it will be connected to the stream processor. Certain work will be done and it will be sent to the producers. The producers are on the other side of the Kafka cluster, which will be producing this data to the consumers. I mean, these consumers are separate. The ones inside the Kafka are separate consumers. So these are the consumer groups or the subscribers, you can say, in the pub sub model. So these producers will be producing to the subscribers. Okay. Let's say that it is producing to multiple workers, which are here, which are in the stream process. Okay. So let's say this is worker 1 So there is worker 2 and so on. There is worker n. Worker n. All these workers, these all are together in the Kafka cluster, considered in the Kafka cluster. And this together is forming the distributor. Distributor's job is to just take something and relay it, send it to somebody else. So let's say these are all the worker nodes who will do data transformation for you. This is inside the Kafka cluster, by the way. So this will do the data transformation for you, just like in the stream process, right? It will do the data transformation for you. These are all processors. Okay, so this is the setup. Now in this case, if you have to produce something, if you want to assign your job to the workers, how will you assign? Let's say there is message 1, message 2, and message 3 coming. Let's say there are worker 2 and worker 3. Only 3 workers are there. What makes sense for your assignment? You will assign one message per worker, maybe, isn't it? Will you go with that? Or will you go with some other option where you say that no, I will assign message 1, message 2, message 3 to all the same worker? Which assignment makes sense?
The first one.
Yeah, I mean, I would want to be fair with all the workers. I don't want to overload a single worker, right? So I will be assigning it to all the workers one by one. Fine, that is correct. That is something I would want to do. But there may be a simple algorithm to do that. Maybe I will want to do this with round robin, isn't it? Can round robin do this thing? Round robin is a very simple algorithm where you just take the message and you just move it top down in a circle, right? So when message 1 comes, it will assign here message 2, message 3. If message 4 comes, it will assign here message 5 and so on, right? So it will go in a round manner. That's why the name is round robin. Okay. So round robin is one way, I think a good way to make the assignment. Either it is to the worker thread or it is to the assigning the data to the partitions, because you know that a single topic can have multiple partitions. So which partition you should stream to do the load balancing there, so that the consumers are not overloaded, because all the partitions are taking the same nature of data. If you happen to stream a single data to all the partitions, then it will load all the worker threads because they are consuming, right? And they are working on it. What is the use of that? Anyway, I will not go to detail. It will just confuse you. But then in the round robin way, if you are doing, I hope you understood what we are doing, right? If you have worker 1, worker 2, worker 3, then we are sending 1, 2, 3 here. And then if we have 4, 5, we are sending like this. Okay, simple. This is the assignment of round robin. But there may be certain scenarios, and generally there are scenarios where you would want to maintain sticky sessions. That I just want to be connected to whichever server in a session. I don't want to switch the servers. Okay, there can be certain requirements for that. So in that kind of situation, I cannot use round robin. Then I have to use the sticky partitioner. And in the sticky partitioner, what it does is, if you have again worker 1, worker 2, worker 3, let's say all the 3 messages have connected to worker 1, and so M1, M2, M3 will all go to the same worker because of the sticky sessions requirement. So if you have that requirement, you cannot do load balancing in this, right? You cannot do load balancing, and there is no avoiding it if you have such requirements. Okay. Now, I don't want to consider this case, because if you had requirement, then only you moved into this scenario. Generally, we don't have this kind of requirement. We are more concerned about the analytics, more concerned about receiving the message rather than being connected to the same server all the time. Generally, this is happening with the browsing information when you are actually doing browsing. But Kafka is not about you being connected to a server while browsing. Okay. So that is different. Anyway, the problem is what? Okay, let me set up the problem. Okay. So now I want to do load balancing. Let's say I sent 3 messages and or let's say 6 messages. I'm talking about 6 messages. So M4, M5 and M6. So I'm talking about 6 messages. You are using round robin. and you have assigned M1, M2, M3, M4, M5, M6. Okay, this seems very correct. This seems very correct. And there are two assumptions which are being used here. The first assumption is all the consumers or the workers have equal strength, have equal processing power. Okay, so they are not distinguishable. That's why you are doing round robin. If some processor, let's say worker 2 is very weak, but worker 1 is extremely strong, then will it be fair to send the equal workload to every worker? It will not be fair. But when you are doing simple round robin, then you are doing this first assumption that all the consumers or workers have equal strength. Okay. The second assumption is all the messages are equal in workload. The messages may not be equal in workload. One message may be trying to connect to the DNS server. One message may be trying to connect to a third party website and trying to load something from there. One message may be trying to connect to a local website. Another message may be trying to connect to a faraway website, which is available somewhere else, not in the cache or in the local cluster. So it will have added network latency. The quality of website where it is hosted will also add on to the latency if it is not a proper hosting. So you cannot say that one message, all the messages will have identical time to process. You cannot imagine that Amazon.com and some XYZ.com will load at the same time and will have the exact same workload. Each messages may have different workload. And they are not, if you draw a graph of workload, okay, if you draw a graph of workload, then each of the messages may have different workload altogether. Okay, they can have different deviation. And if you just draw a graph, like it will be something like this. But ideally, what we are assuming is every message has the same workload. And so if I split equal number of messages, then I will be good, but I'll not be good. In this case, if you just see about assigning these 6, 1, 2, 3, 4, 5, 6, 7, I think 7. Okay. So if you think about assigning these 6 items, then which item do you assign? If you assign these first two to somebody, let's say you assign these two to somebody and these two to somebody, then this will be very less loaded. This will be very high loaded. Let's say this went to the best worker. This went to the worst worker. Is this a good strategy to do? This is the worst case scenario. That the most load can go to the least performing processor, and the least load can go to the the best performing processor, isn't it? So this simple round robin doesn't work in our case. Anyone available? Or everybody is sleeping? Okay. So I think, does this make sense now that the simple round robin is not a good strategy to do? And so Kafka doesn't use simple round robin approach in this case for doing load balancing. Okay. Are we clear? Like, why don't we use simple load balancing?
Yeah. Yes.
Okay. Then what makes sense? I mean, generally, if you want to maintain, let's say you will argue that, let's say, why can't we maintain equal strength of each worker? Each worker can have same configuration of hardware, and so they will be easy to manage, isn't it? At least one factor I can remove by maintaining same hardware. But the first thing is, I'm assuming you have large number of workers because you have already scaled. That's why you are using Kafka, and that's why we are doing load balancing and all these things, considering you have high number of requests and high number of workers to handle those requests. Now let's assume that everyone has the exact same processor. Okay, let's say Intel 7 processor. Everyone has this. Let's say if you want to upgrade, then you have to upgrade everyone. It will be a very costly upgrade actually. If you want to replace something, you cannot make somebody i9, you cannot make somebody i10, 12, 13, whatever. But if you want to upgrade, you have to move forward equally, and that will increase the cost a lot. It will be very less flexible. You want more flexibility in terms of hardware. And whenever we discuss about horizontal scaling, then we discuss about commodity hardwares and independently upgrading. You don't want it to be too highly dependent and coupled together, so that if there is only one update, everybody has to update. So if you have to only update one processor, you have to update thousands, hundreds of thousands of processors. So you want that to happen. Maybe that is something I don't want to happen. So I will not touch the head to maintain homogeneous hardware, or is everyone maintaining equal strength, but I will always assume that there is heterogeneous hardware where the hardwares can be different everywhere. I don't want to maintain that, isn't it? So this point I cannot maintain myself. What about the messages being equal workload? Now this also you cannot handle, because the producers are producing something. How will you handle that? And you will not know what is the workload unless you perform that work.
Yeah.
Otherwise, how will you know it, right? There is no way you can know it. So this also is not under your control. So these two things are not under your control. So what would be the best strategy? Definitely round robin is not a best strategy. Sticky partition, there is no option in that. If the application requires it, you have to do it without the consideration of load balancing a lot. If you have to do load balancing, you have to think initially which server I'm connecting to. I should connect to the least loaded server at the time of connection, because sticky session will maintain the entire session with the same worker. So I don't want to start a sticky session with the high workload worker. I mean, why do you want to do that? It doesn't make sense, right? So there has to be some kind of sensing algorithm which can actually sense and say, or it can maintain a priority of where I should make the assignment based on the load. You can maintain a priority queue of the workers. You can write your own custom logic and maintain an entire priority queue of the worker IDs to which you will make the assignment. So you have to also keep track of the load. So the zookeeper will keep track of all these task manager stuff. This is the coordinator's job, that it will keep track of who is loaded at what level. Is it 90% CPU usage, 30% CPU usage, how much RAM is getting used, what is happening? And based on that, it will maintain a priority list. And whenever a request comes in, it will assign it based on the priority list. Does this make sense now? Does this make sense? Okay, this is one solution. If you are thinking about, let me give you another example. I think the answer was clear to you. One of the answers, not just, or it is not the absolute answer. It is just one of the answers. Okay, if the zookeeper maintains, it have to keep on monitoring the workload on all of the workers and maintain a priority list or priority queue of which one is the next best assignment, which worker should get the next best assignment. It may maintain multiple priority queue lists depending on different type of servers, different type of topics, right? Different type of groups as well. It can maintain different priority list. That is fine. So let me give you another example. Let's say there is consumer. I hope we are not going too much in time. So it is already beyond 10, which is way beyond our expectation, right? And there is producer. So this is inside your distributor. Distributor is within the Kafka cluster. It receives, consumer receives, and producer distributed to the worker nodes. So let's say there you have the partitions of the Kafka. P1, P2, P3, P4, P5, and P6. Let's say you have all these 6 partitions. Just setting up an example and showing you a different problem in Kafka and how it is solved. So this is, let's say, the topic. Let's say topic 1 has 6 partitions. Okay. Now there are different workers who will perform a certain kind of job. Let's say there is worker 1, worker 2, worker 3. Okay. Let's say that this worker is good worker, this worker is good, this worker is a bad worker. Let me make it in red. Bad worker is maybe it is not performing as expected. So let's say the performance of each of them is 25 messages per second. Same 25 messages per second. I'm saying is bad because it is comparatively less performing as compared to worker 1, worker 2. Maybe its hardware is also not, it is using Pentium processor, who knows? So it is performing less, okay, out of any reason. I don't know what is the reason. So let's say that these are the assignments being done. These are the partition assignment to the worker threads. So these are the worker. This entire thing is within the Kafka cluster, by the way. Okay. This entire thing is within the Kafka cluster. I hope I have already explained all these things, right? Within the Kafka cluster. Messages are coming from one end. It will be published only when the workers do the data transformation according to whatever pipeline you have written on the partition, and from the partition, it will be streamed to the other consumer. So consumer groups are on the rightmost side. It is not shown. Leftmost side, incoming messages from here, it is not shown. Outgoing messages from here, it is not shown. DB is also not shown. Okay. But I am just concerned about this problem. Let's say that in this case, all these are giving 10 messages, writing 10 messages per second. 10 messages per second, 10 messages, 10 messages, 10 messages. Purnima, are you available?
Yes, yes.
Okay. So let's say these 10 messages per second are being written to all the partitions. Okay. Now in this case, don't you think that these are 60 messages per second and they should be able to handle it? Will they not be able to handle it? They should be able to handle it. But then the assignment, you see the assignment. Two partitions we have given to each worker. Now the problem is the first guy is getting 20 messages, and can it process it? Yes. Second guy is getting 20 messages. Can it process it? Yes. The third guy is getting 20 messages, and the lag it gets is equals to 10 messages per second. Right? 10 messages per second. If you have these two type of workers available with you, then how many more workers will you add so that you will guarantee there is no lag? Even after the workers become bad, there will be no lag. What will you do?
We can add one more worker.
Okay. So we will not just add one more, but we will add 3 more
Okay.
to guarantee that even if the worker becomes bad, my jobs will go through, because you have to process 60 messages per second. You have 3 workers in place. Yes, 2 are performing well, 1 is not performing well. But I said that I have to guarantee that even if people, the workers become bad, still my my message processing is guaranteed. So I will add 3 more workers, worker 4, worker 5, worker 6, each with maybe capacity of 25 messages per second. This may have slowed down due to some reason, but let's say all were somewhat same. But you see that if you make such kind of assignment, you are actually doing over provisioning or over allocating, right? This is the over provisioning issue, where if you want guarantee of processing, then you see who is the least performing worker, and based on that you calibrate how many workers do you need, because any worker can become least performing. But by using this technique, you are over allocating your resources most of the time to provide this guarantee. So this is your over provisioning issue. Do you want to get rid of this issue or what? I mean, I don't want to have this issue because this is very costly. This is allocating a lot more resources than I actually need in real time. So this algorithm is actually not as good as it looks. I mean, it doesn't look good also, isn't it? This is one algorithm which is available, but this is not a good option. The previous option with the priority list was much better than this option. This is the second algorithm. Let's see the third option that you can have. The third option you can have is about the lag aware algorithms. It is called lag aware algorithm. So in the lag aware algorithm, there is always a sensor. There is always a sensing process. So there is lag aware producer and there is a lag aware. This is the set of workers. So lag aware consumers, lag aware consumers, I will say. The workers in this case are, I mean, the producer and consumers are within the same Kafka cluster here. It is not the consumer group, but then lag aware consumer and lag aware producer. The lag aware producer, what it does is, if it senses that I'm overloading the partitions, let's say this partition 1 is getting too overloaded because the consumption rate in P1 is seemingly smaller. I'm producing 10 messages and it is consuming only 5 messages. What it does is, let me give an example. The lag aware, let's say here it is maintaining the lag aware, whatever option is this, lag aware metadata or something, some coordinator is running, okay, and it is taking all the information. Generally Zookeeper maintains all these things. So in this case, when 10 messages are being sent to everybody, because I wanted load balancing, then what happened was 10 messages was consumed here, consumed here, consumed here, consumed here, consumed. But will it be consumed at these two places? It will not be consumed. Let's forget about this. Okay. It will not be consumed. And if it is not consumed, how many are consumed? Let's say 5 messages from here and 5 messages are from here are consumed and 5 are lagging too. Then what will this lag aware, coordinator will do is, it will send 5 less messages to P5 and 5 less messages to P6. And it will redistribute it over P1 to P4 equally. How many messages it has to redistribute? 10 messages. So maybe it will send 3, 2, 3, 2 to the others. And with this redistribution, can we handle the load? Now this will get 25, this will get 25, but still they can process it. And this will start getting 10, and this will be also able to process it. So this lag aware option from the producer side is making intelligent decision on, if somebody is lagging, let's redistribute his or her load to someone else, right? Because maybe some other processors must be better performing and they still have, some load to spare, some work load to spare, right? So if you look at the other groups, if they were actually running at full capacity, then they will start lagging. And if they start lagging again, it will sense and rebalance it to and send it to someone who is not lagging. After a certain time, if it feels that I am trying too much and many people are lagging, then it will slow down the production rate. It will store on its own side. It will slow down the production rate. Okay. So that is lag aware option on the producer side. On the consumer side, if it also maintains lag aware stuff by saying that if I can consume more, I will probably request more if you want me to process more. It will say that, yeah, I could process 20, but I can take 5 more load. So it will be coordinating and sending it to the other side. If you want to produce more, you can produce more because I can handle more. Okay. And if the producer wants to produce more somewhere, then it can produce. So all this coordination, there has to be a central coordinator who knows about the producer, who knows about the consumer, and who knows about where what is happening. So this central coordinator is your zookeeper, who actually talks to everyone and maintains everything together. Okay. So this option is the best option, and this option is in production. This lag aware option, because this is sensing and doing rebalancing. Now, this is not the only thing they do. They do dynamic partition management too. Now, if the partitions are overloaded, then they may add another partition P7 and they may add another partition P8. And they may add other, this is called dynamic partitioning. Okay. And they can also remove some partition if it is not needed and add it to the pool simply. If you want to leave it, you leave it. So dynamically, you can scale up or scale down in the number of partition. This is called dynamic partitioning. Then there is auto balancing feature in Kafka. The auto balancing feature is about the worker side, and also about, I mean, this lag aware stuff is the implementing the auto balancing. In the auto balancing, the workers are saying, I can take more. So you can, if you want, you can send me more. It is saying to the zookeeper. Now, zookeeper is telling to the producer that these guys are having some capacity, and this is the capacity they have advertised to me. They have told me that they can take this much of load. If you want to say, I mean, they will not say I will take this much load or that much load. They will just share the metric. Like I am 50% loaded. So you decide how much I should be loaded. Now the zookeeper knows that I should load till 80% safely. So it will say the producer that you can send 30% more messages than what you are sending to W1. So this is your auto balancing feature. And not just this, you can definitely add more workers to do auto balancing. But with the same number of workers, this is how auto balancing can be done. Are we clear? This is rebalancing or auto balancing. So in Kafka, you have dynamic partitioning, you have auto balancing or rebalancing, and you have lag aware producers and lag aware consumers. These all entire thing is in the Kafka cluster. On the left side, you have the producers, actual producers of messages. Don't confuse the actual producer with this producer consumer and this consumer. This is just local producer consumers, right? This is all within the Kafka cluster. So do you get some idea about the architecture of Kafka? I hope so. Was it good enough according to your expectation, or what do you think?
Yeah, it is more than the idea.
There are other algorithms too. Let's finish it up with two more. Those are simple algorithms, but this is the most important one, the lag aware systems. And the load balancing, auto balancing, rebalancing, and the dynamic partitioning is the important feature of Kafka. So that's why we took time. This is the first time I'm discussing. So that's why I took Kafka again. I have been taking this in the past two batches, but never explained this thing out of time. People don't want to spend time into this thing, right? But since you guys seemed eager enough to actually extend the time, and actually three people are left only, so I just did that because I will be more excited to share more information rather than half information, right? That I've been sharing in the past two batches, two, three batches. But anyway, let's move to the last part. Okay. Last option, this third option is the best option according to me. I will always go with that, and Kafka actually implements this thing. But what other options can you have? Other proposals. Other proposals are same length queue. So same length queue is again based on the number of messages. Like let's say there is a producer. You can see it on this side. This is the producer I'm making. So this is the producer part. Now the producer is sending to the partitions. Let's say partition 1, partition 2, partition 3, partition 4. Okay, fine. It is sending to multiple partitions. And then when it is sending to all the partitions, you see that at any point of time, if this has 4 load, if it has 1 load, if it has 3 load, and if it has 2 items, 2 load, then the next message which is coming should go to partition 2. This is actually the first answer that we had thought of. That is based on number of messages you do balancing. and this same length Q is the same thing. It is just a different name, but the same thing. But then we already discussed about the problems. Each message can have different workload, each hardware can be different, and many other things can happen. So that's why we already rejected this option. And that's why we adopted the lag aware system, which is in real time adapting according to what is happening in real time. And that makes sense. This is more practical. Third option is more practical. This is lag aware system. Then there is fifth type as well, which is by doing outlier detection. So this is outlier detection algo. Okay. You don't have to remember the algo. It is just about options. I mean, you understanding the things is like, even if you can remember 20-30%, it's good enough, I would say. More than good enough, right? So in the outlier detection algo, what it does is it will categorize the partitions into slow partition, into okay partition, and into good or healthy partitions. How does it see that? Mainly if you can elaborate your data points. Okay, if your data points is this is the zero data point, and this is the 100 percentile data point, this is the 0 percentile data point, then within this you can always make a interquartile range where you will have this as 75th percent, this is quarter 3, and this is quarter 1 saying 25th percent. Okay, this is quarter 1, and there may be somewhere here, let's say 50th percentile as median, which is Q2. Then if the data point, if your load is lying outside of Q3 or outside of Q1, there you are an outlier. If your load is below Q1, you are very less loaded. If your load is beyond Q3, you are very high loaded, and you are not a healthy. So maybe here I will say okay load. Here I will say very good partition. I mean, allocate more messages to this guy. And here I will say it is a slow kind of partition. So maybe slow down your messages here, reroute your messages to somewhere who are good or okay. Don't send it to the slow partitions, right? Because it may crash, or you may lose the messages, or it may take more time to process because it has so many other things to do. Are we clear? Are we clear? So this is, I mean, this is simple, right? This is simple. So you can just maintain a partition lag. You can always check or sense the partition lag, how much it is lagging, and you can compare it with the time t from all the data points, that you have plotted on the scale, and you can take the minimum of your IQR, which is the interquartile range, comma your standard deviation. This is just a mathematical figure. If your standard deviation has a formula too based on the data points, if it is going beyond the standard deviation, let's say this is the standard deviation. If it is going outside of the standard deviation, it is an outlier point. So maybe the current partition is lagging more, or it is very much better. You can detect outliers like that, or you can follow this interquartile range technique, or you can just include them together and take the minimum of whatever it is and just compare it with the partition lag. So if the partition lag is more than this, it is lagging. If it is less than that, it is good. Something like that. Okay. So I don't want to discuss more. A lot of things are there in Kafka, but I think more is not required.
Question. So, is there a chance of DDoS in Kafka?
Huh?
Is there any chance of DDoS in Kafka?
Is there any chance of that one word?
Duplication.
What word it is? I mean, I'm not getting this. Is
He's
there
asking
any
about the
chance?
duplication of Kafka.
Duplication in Kafka?
Yes.
Yeah, I mean, replication is there, right? So what do you mean by duplication, by the way?
No,
I think she's asking about the message duplication. Like,
Oh, to the consumer side?
Uh, in both side actually.
Let me go back to the
So
figure.
if she is if I'm
This one.
understanding correctly, so what she's trying to say, if you are publishing a message to Kafka,
Ah.
is there a way like uh, can it happen multiple times? Like can we publish the same message multiple times?
Yeah, I mean that we discussed, right? I mean there were some
Yeah.
guarantees we were discussing, right? That it depends on what type of guarantee you are doing. Depending on that, you can have multiple times, one time, or whatever times. These guarantees we have discussed, right? At most once, how to do it? At most once, at least once, and exactly once, isn't it? Is this clear? I mean, depending on this, like if you are taking at least once, then you can have it multiple times.
So Kafka take every single message a different message. That's what.
Oh,
So
every
even if
single
you're
message has different message. Yes, every single message, different messages.
so even if you are publishing same message 100 times, Purnima, it will be like duplicate
Depends.
for 90.
Again, it depends. If you are maintaining exactly once, then I said that,
Yeah.
okay,
Yes. Yes. No.
I
I'm
think
just trying to answer her question.
okay, your
So
answer.
yeah.
This covers the answer, right?
Yes. Those three, one of those three, or
It
all
depends
three
on what
cover
choice
that
you have
answer.
made. Yeah. Tomorrow's class will not be this long. So it will be 2 hours within 2 hours. I will try to maintain that. I will not go
But today
overboard.
is like almost 3 hour 10 minute.
Yeah, that's what I was saying, that I should
So
be quick.
when you will upload this video? Today, tomorrow?
When do you want it? Today, if you want, I can upload today.
No. So not
But
today. I don't want today. But the problem is like after tomorrow.